The Mariana Trench is the deepest part of the Pacific Ocean. It stretches for more than 1,500 miles. Its deepest point, Challenger Deep, reaches nearly 7 miles below sea level, which is deeper than Mount Everest is tall above sea level. At that depth, the water pressure is more than 1,000 times greater than at sea level. The temperature is near freezing, and no sunlight reaches that level. The conditions can damage or crush most equipment that is not specially designed. Only a small number of humans have traveled to the bottom using advanced submersibles. Even in these harsh conditions, scientists have discovered living organisms. But what makes the Mariana Trench truly dangerous? The Pacific Ocean is already the largest and deepest ocean on Earth. Yet even within this giant body of water, the Mariana Trench stands out as something extraordinary. At Challenger Deep, the trench reaches a depth of about 36,000 feet below sea level. To understand how deep that is, imagine placing Mount Everest, the tallest mountain on land, into the trench. Even Everest, which rises more than 29,000 feet above sea level, would still have over a mile of water above its peak if it were placed inside the trench. That comparison alone shows how unbelievably deep this place is. But how did such a deep and dramatic feature come into existence? The answer lies in the powerful and slow-moving forces beneath Earth's surface. Our planet's outer shell, known as the crust, is not one solid piece. Instead, it is broken into large sections called tectonic plates. These plates float on the semi-molten layer beneath them, called the mantle. Over millions of years, these plates move, collide, pull apart, and slide past one another. Their movements shape continents, form mountains, trigger earthquakes, and create ocean trenches. The Mariana Trench was formed by a process known as subduction. Subduction happens when one tectonic plate is forced beneath another. In the case of the Mariana Trench, the Pacific Plate is being pushed beneath a smaller plate known as the Mariana Plate. As the heavier Pacific Plate slides downward into the mantle, it bends and sinks. This bending creates a deep depression in the ocean floor. Over an incredibly long time, this depression became deeper and deeper, forming the trench we know today. The process of subduction is slow, but it is relentless. The Pacific Plate moves only a few inches each year. That might not sound like much, but over millions of years, those small movements add up to enormous changes. Imagine pushing a thick rug slowly under a heavy piece of furniture. Over time, the rug would wrinkle and fold. Something similar happens with tectonic plates, except the forces involved are far more powerful and operate on a planetary scale. As the Pacific Plate sinks beneath the Mariana Plate, it drags part of the ocean floor downward with it. The point where the two plates meet is known as a subduction zone. Subduction zones are some of the most active geological areas on Earth. They often produce powerful earthquakes and volcanic activity. In fact, the Mariana Islands themselves were formed by volcanic activity caused by this same subduction process. When the sinking plate melts deep within the mantle, magma rises toward the surface and forms volcanoes, some of which break through the ocean's surface to create islands. The shape of the Mariana Trench is not a simple straight line. Instead, it curves in a graceful arc, following the boundary between the two plates. This arc shape is common in many subduction zones around the world. However, what makes the Mariana Trench special is not just its shape, but its incredible depth. Challenger Deep, the lowest point within the trench, lies in its southern part. It was named after the British survey ship HMS Challenger, which first measured the depth of the trench in the late 19th century. At that time, the crew used weighted ropes to measure the ocean's depth, a slow and difficult process. Their measurements showed that the ocean floor dropped far deeper than anyone had previously imagined. Later, more advanced equipment confirmed that Challenger Deep is the deepest known point in Earth's oceans. The depth at Challenger Deep is so extreme that the pressure there is almost impossible to imagine, Water pressure increases as you go deeper because more water is stacked above you. At the surface, we feel only the pressure of the air, but at the bottom of the Mariana Trench, the pressure is more than 1,000 times greater than at sea level. It is equivalent to having dozens of jumbo jets stacked on top of you. No ordinary submarine or diving suit could survive such crushing force. Only specially designed vehicles can descend to those depths. The formation of the trench also tells us something important about the age of the ocean floor. The Pacific Plate, which is being pushed down into the mantle, is very old compared to some other oceanic plates. As oceanic crust ages, it cools and becomes denser. Because it is denser, it is more likely to sink beneath another plate when they collide. This is one reason why the Pacific Plate is subducting beneath the Mariana Plate instead of the other way around. Over millions of years, as the Pacific Plate continues to sink, it carries sediments, water and minerals down into the mantle. This recycling of Earth's crust is part of a continuous process known as the rock cycle. In this way, the Mariana Trench is not just a deep hole in the ocean floor. It is part of a larger system that constantly reshapes our planet. Materials from the surface are drawn down into the Earth, where they may later return through volcanic eruptions. The trench also plays a role in the movement of water and heat within the ocean. The deep waters of the Pacific are cold and dense. They slowly circulate around the globe in a system known as thermohaline circulation. While the Mariana Trench itself is only one small part of the ocean floor, its extreme depth influences how water masses move in that region. Geographically, the trench marks the boundary between two major sections of the ocean floor. To the east lies the vast Pacific Abyssal Plain, a relatively flat and deep region. To the west are the Mariana Islands and the smaller Mariana Plate. The sharp drop from the surrounding seafloor into the trench is dramatic. It is as if the ocean floor suddenly falls away into a giant chasm. Despite its remote location, the Mariana Trench has captured the imagination of scientists, explorers, and the public for decades. Its formation through tectonic forces provides strong evidence for the theory of plate tectonics, which became widely accepted in the 20th century. Before scientists understood plate tectonics, the existence of such deep trenches was difficult to explain. Now we know that they are a natural result of moving plates and subduction zones. The trench's depth also reminds us how little of our planet we have fully explored. Humans have walked on the moon, yet only a handful of people have visited the deepest part of the Mariana Trench. The darkness, cold temperatures and crushing pressure make it one of the most extreme environments on Earth. Yet it exists quietly beneath the waves, largely hidden from everyday life. The western Pacific region where the trench lies is one of the most geologically active areas on Earth. It is part of what is often called the Ring of Fire, a zone around the Pacific Ocean known for earthquakes and volcanic eruptions. The constant movement of tectonic plates in this region continues to shape the seafloor and the islands above it. Even though the Mariana Trench is already the deepest known part of the ocean, it is not static. The tectonic plates are still moving. The Pacific Plate continues to slide beneath the Mariana Plate, very slowly but steadily. Over extremely long periods of time, the trench may become slightly deeper, or its shape may change. Geological processes operate on timescales far beyond a human lifetime. When we think about the Mariana Trench, it is easy to focus only on its record-breaking depth, but its true importance lies in what it teaches us about Earth itself. It shows us that our planet is alive with movement beneath its surface. The ground beneath our feet and the ocean floor beneath the waves are not fixed and unchanging. They are part of a dynamic system driven by heat from Earth's interior. The formation of the Mariana Trench began tens of millions of years ago. As the Pacific Plate moved westward, it eventually met the edge of the smaller plate. The heavier Pacific Plate began to sink. Over time, the bending of the plate created a deep groove. Sediments from rivers and ocean currents settled into the trench. while earthquakes shook the region as the plates ground against each other. The trench is shaped somewhat like a steep-sided valley. The slopes leading down to Challenger Deep are rugged and uneven. Landslides sometimes occur along these slopes, triggered by earthquakes. These underwater landslides can send clouds of sediment drifting through the deep water. Because the trench is so deep, sunlight cannot reach its bottom. The ocean becomes completely dark at depths of about 3,000 feet. Challenger Deep lies more than 10 times deeper than that. In this total darkness, the geography of the trench remains hidden unless illuminated by artificial lights from submersibles. The temperature at the bottom of the trench is just above freezing. Combined with the immense pressure, this creates one of the harshest environments on the planet. Yet life has been discovered even there, proving that Earth's ecosystems can adapt to extreme conditions. The name Mariana comes from the nearby Mariana Islands, which were named after Queen Mariana of Spain in the 17th century. These islands form an arc that mirrors the curve of the trench. Their volcanic origins are directly linked to the subduction process that created the trench. The more scientists study the Mariana Trench, the more they learn about Earth's deep processes. By examining rocks and sediments from the trench, researchers can gain insight into how plates move, how materials are recycled into the mantle, and how earthquakes are generated. The trench also challenges our understanding of limits. It represents the lowest known natural point on Earth's surface. While mountains rise high into the sky, trenches plunge even farther downward into darkness. In a sense, the Mariana Trench is the opposite of a mountain range. Instead of being built upward by forces pushing rock toward the sky, it is formed by forces pulling rock downward into the planet. The Mariana Trench exists because Earth's surface is broken into moving pieces. Where those pieces collide and one sinks beneath the other, a deep trench forms. Over millions of years, that trench can grow deeper and more defined. The Mariana Trench is the most extreme example of this process known to us. The deep ocean is one of the most extreme places on Earth. It is not extreme because of fire, explosions, or violent storms. It is extreme because of weight. The deeper you go beneath the surface of the sea, the more water piles up above you. That water is heavy, and its weight pushes down with an invisible but powerful force called pressure. At the deepest parts of the ocean, this pressure rises beyond 1,000 atmospheres. That means the force pressing on a body is equal to the crushing weight of about 50 jumbo jets stacked on top of one person. It is a level of pressure so intense that it can flatten metal, crack thick glass, and destroy unprotected equipment in an instant. To understand how serious this pressure is, it helps to start with something familiar. At sea level, where people live, the human body experiences 1 atmosphere of pressure. That pressure comes from the air pressing down from above. We do not feel it because our bodies are built to handle it. The air presses inward, and the fluids and gases inside our bodies push outward with equal force. Everything stays balanced. Now imagine diving underwater. Even a short dive increases pressure. For every 10 meters you descend, the pressure increases by about 1 additional atmosphere. That means at 10 meters below the surface you experience 2 atmospheres of pressure. At 20 meters, 3 atmospheres. At 100 meters, 11 atmospheres. The increase is steady and relentless. The deeper you go, the more water is stacked above you, and the more crushing force pushes inward from every direction. At the deepest known point in the ocean, located in the Mariana Trench, pressure reaches levels beyond 1,000 atmospheres. This deepest section is often called the Challenger Deep. It lies nearly 11 kilometers beneath the ocean's surface. At that depth, every square inch of surface area experiences thousands of pounds of force. If a person could somehow stand unprotected at that depth, the pressure would collapse their lungs instantly. Bones would crack. Air spaces in the body would shrink to almost nothing. The human body is not designed to survive such an environment. To visualize 1,000 atmospheres, imagine 50 large commercial airplanes stacked on top of you. Each jumbo jet weighs hundreds of tons. Multiply that weight again and again until the total force presses evenly from every direction. Each jumbo jet weighs hundreds of tons. Multiply that weight again and again until the total force presses evenly from every direction, not just from above. That is an important detail. Ocean pressure does not push down only from the top. It pushes from the sides and from below as well. It surrounds everything completely. There is no escape from it. There is no weak side where the force is lighter. It is equal and crushing in all directions. This pressure creates enormous challenges for equipment. Submarines designed to explore the deep sea must be built like armored vaults. Their hulls are often made from thick steel or special titanium alloys. The shape of the vessel matters just as much as the material. Spheres are commonly used for crew compartments because a sphere distributes pressure evenly. There are no corners where stress can build up. Every curve helps spread the crushing force. One of the most famous deep-sea vessels, the Trieste, made a historic descent into the Mariana Trench in 1960. It carried Jacques Picard and Don Walsh to a depth of nearly 11 kilometers. The crew compartment was a thick steel sphere with walls more than 12 centimeters thick. Even with that protection, the vessel creaked and groaned under the immense pressure. At one point, a window cracked, creating a loud bang that startled the crew. Yet the sphere held, proving that with careful design and engineering, humans could survive briefly in such crushing conditions. More recently, the submersible named Deep Sea Challenger, piloted by filmmaker James Cameron in 2012, also reached the Challenger Deep. This vessel was built with advanced materials and careful engineering to resist the extreme pressure. Even so, engineers spent years testing and redesigning parts to ensure they would not collapse under the immense force. Pressure affects more than large submarines. Even small pieces of equipment face danger. Cameras, lights, robotic arms, and scientific instruments must all be specially designed. Regular electronics would fail quickly because seals would break and water would rush in. At great depths, even tiny flaws can lead to catastrophic failure. A small crack becomes a fatal weakness when thousands of atmospheres press against it. The pressure also affects gases in dramatic ways. Airspaces shrink as depth increases. This is why scuba divers must carefully manage their breathing. At great depths, gases like nitrogen can dissolve into the bloodstream in dangerous amounts. When divers ascend too quickly, those gases can form bubbles in the body, causing a painful and sometimes deadly condition known as decompression sickness. Professional divers train extensively to understand these risks, but even they rarely go beyond a few hundred meters using special equipment. Below a certain depth, human divers cannot operate at all. Instead, remotely operated vehicles and autonomous underwater vehicles are used. These robotic explorers send back images and collect samples. They move slowly through the darkness, their lights cutting narrow beams through the black water. Outside their metal shells, the crushing pressure remains constant and unforgiving. Despite this extreme pressure, life exists in these depths. That fact alone is astonishing. Creatures have adapted to survive under forces that would instantly destroy humans. Fish, crustaceans, worms, and strange gelatinous organisms move slowly along the seafloor. Some look fragile and soft, yet they thrive in an environment of unimaginable weight. One reason deep-sea creatures can survive is that their bodies do not contain large air-filled spaces. Without air pockets, there is less for pressure to crush. Many deep-sea animals have flexible bodies made mostly of water, which does not compress easily. Their cells contain special molecules that stabilize proteins and prevent them from breaking down under high pressure. Scientists have discovered organisms living near deep-sea hydrothermal vents, where hot, mineral-rich water pours from cracks in the seafloor. These vents exist thousands of meters below the surface, The combination of heat, toxic chemicals, total darkness, and crushing pressure makes these areas some of the harshest environments on Earth. Yet entire ecosystems flourish there. Tube worms, shrimp, and unique bacteria form complex communities that do not rely on sunlight. Instead, they use chemical energy from the Earth itself. Pressure changes the chemistry of life. Enzymes, which drive the chemical reactions in cells, behave differently under high pressure. Proteins can lose their shape. Membranes can become too rigid. To survive, deep-sea organisms produce special compounds that help maintain flexibility. Their bodies are fine-tuned to operate in conditions that would break the biology of surface creatures. The crushing force of the deep also shapes the landscape. Sediments are compacted tightly under the weight of water. The seafloor can experience powerful geological forces. In subduction zones, one tectonic plate slides beneath another, creating deep trenches like the Mariana Trench. Earthquakes occur even at these depths, sending shockwaves through water and rock alike. Sound behaves differently under pressure as well. In the deep ocean, sound travels faster and farther than in air. Many deep-sea creatures rely on vibrations rather than sight, since sunlight does not penetrate beyond about 1,000 meters. Below that depth, darkness is complete. Bioluminescent organisms create their own light, glowing blue or green in the black water. These flashes are signals, lures, warnings, or tools for hunting. Human curiosity has pushed explorers to continue studying these extreme depths. Each mission reveals new species and new insights into how life can adapt. Understanding how organisms survive under 1,000 atmospheres of pressure can help scientists learn about the limits of life itself. It also has implications for the search for life beyond Earth. Moons like Europa, which orbits Jupiter, are believed to have oceans beneath thick layers of ice. If life can survive under crushing pressure in Earth's oceans, perhaps it can exist in similar environments elsewhere in the solar system. Engineering for extreme pressure has improved over time. Materials such as advanced ceramics and carbon fiber composites are tested in pressure chambers that simulate deep ocean conditions. In these chambers, machines pump water into thick containers, raising pressure gradually until it matches that found kilometers beneath the sea. Equipment is monitored closely. Engineers look for bending, cracking, or failure. The lessons learned from deep-sea exploration have practical uses. Oil and gas drilling operations often take place in deep water. Cables that carry internet data across continents lie on the seafloor. All of these systems must survive long-term exposure to high pressure. Even a small leak or structural weakness can cause massive financial and environmental consequences. The crushing force of the deep ocean reminds us how small and fragile humans are compared to the forces of nature. On land, gravity feels steady and manageable. In the sky, aircraft overcome air pressure with clever design. But underwater, especially at extreme depths, nature dominates completely. Without protection, survival is impossible. And yet, life finds a way. In darkness and under crushing weight, creatures move, feed, reproduce, and evolve. Their existence challenges assumptions about where life can survive. It shows that pressure, no matter how extreme, is not an absolute barrier. Instead, it is a condition that demands adaptation. Imagine a place on Earth where the sun has never shone, where no sunrise has ever painted the horizon, and no sunset has ever faded into evening. Below 1,000 meters in the ocean, natural light completely disappears. It does not matter whether it is noon or midnight above the waves. Down there, it is always the same, an endless, unbroken darkness. This is a world of perpetual night, a vast environment that covers more of our planet than any forest, desert, or mountain range. It is silent, cold, crushing, and almost impossible to reach, yet it is alive. Sunlight is one of the most important forces on Earth. On land and in shallow water, it drives life. Plants use sunlight to make food through photosynthesis. In the upper layers of the ocean, tiny drifting organisms called phytoplankton do the same. These microscopic life forms form the base of the marine food chain. Small animals eat them. Fish eat the smaller animals. Larger fish eat those fish. Sharks and whales may sit at the top of that chain. Almost every living creature in sunlit waters depends directly or indirectly on light from the sun. But once you pass below 1,000 meters, sunlight is gone completely. Even before that depth, light begins to fade. Around 200 meters down, most of the red light has already disappeared. Deeper still, oranges and yellows vanish. By the time you reach about 1,000 meters, there is no natural light left at all. This region is often called the midnight zone. It is not a poetic exaggeration. It is truly midnight every second of every day of every year. The absence of sunlight changes everything. First, there is no photosynthesis. Without light, plants cannot grow. Phytoplankton cannot survive. That means the usual base of the food chain does not exist. So how does life continue? How can creatures survive in a place where the primary source of energy is missing? The answer is both simple and astonishing. Life in the deep ocean depends on what falls from above or on energy that comes from the earth itself. From the upper layers of the ocean, bits of organic matter slowly drift downward. Dead plankton, tiny particles of waste, fragments of seaweed and the remains of animals sink through the water column like a slow snowfall. Scientists sometimes call this marine snow. It may sound beautiful, but it is actually the remains of life from above. This constant rain of particles becomes food for deep-sea creatures. It is not much, and it falls slowly, but over time it is enough to support entire ecosystems. Occasionally, something much larger sinks down. When a whale dies near the surface, its body eventually sinks to the seafloor. A whale fall can create a sudden feast for deep-sea life. Sharks and large scavengers may feed first. Then smaller animals arrive. Bacteria begin to break down the bones. A single whale carcass can support life in one area for decades. In a world where food is scarce, such an event is extraordinary. But there is another source of energy that does not depend on sunlight at all. In certain places on the deep ocean floor, cracks in the Earth's crust release superheated water filled with minerals. These are known as hydrothermal vents. Instead of using sunlight, special bacteria around these vents use chemicals from the Earth to create energy in a process called chemosynthesis. These bacteria form the base of a unique food web. Around hydrothermal vents, entire communities of strange and remarkable creatures can be found: giant tube worms, unusual crabs, and pale shrimp. These ecosystems prove that life does not always need sunlight. It can survive using the heat and chemicals from deep within the planet. The darkness below 1,000 meters does more than remove sunlight. It shapes the bodies and behaviors of the creatures that live there. In a world without light, vision becomes less important. Some animals have extremely small eyes, and some have none at all. Others, however, have evolved enormous eyes. These large eyes are designed to capture even the faintest glow, because even though sunlight does not reach these depths, light is not completely absent. Many deep-sea creatures produce their own light in a process called bioluminescence. Bioluminescence is one of the most fascinating adaptations in the deep ocean. Through chemical reactions inside their bodies, certain organisms create light. It can appear as a soft blue glow, a flash, or a flicker. Fish, jellyfish, squid, and even tiny plankton can produce light. In the darkness, this glow can serve many purposes. It can attract prey. It can confuse predators. It can help individuals find mates. In some species, patterns of light act almost like a language. Imagine swimming in total darkness and suddenly seeing a blue spark in the distance, then another, then a line of glowing dots moving silently through the black water. That is daily life in the deep sea. The darkness is not empty. it is filled with hidden signals. Because food is limited, deep-sea animals often grow slowly and conserve energy. Many have soft, fragile bodies. Some have enormous mouths and expandable stomachs, so they can eat anything that comes their way, even if it is larger than they are. When a meal might not come for days or weeks, you cannot afford to be selective. Temperature is another powerful force shaping life below 1,000 meters. The deep ocean is cold, often just a few degrees above freezing. This cold slows down metabolism. Creatures move more slowly. Growth happens gradually. Life proceeds at a different pace compared to the busy, brightly lit waters above. Pressure is also extreme. At 1,000 meters below the surface, the pressure is already immense. As you go deeper, it increases further. Every 10 meters of depth adds more pressure. By the time you reach several thousand meters, the weight of the water above is crushing. For humans, such pressure would be deadly without protection. Our bodies are not designed for it, but deep-sea creatures are built for this environment. Their bodies contain no air-filled spaces that would collapse. Their cells are specially adapted to function under high pressure. To them, this crushing force is normal. The absence of light and the presence of high pressure and cold create one of the most challenging environments on Earth. Yet life not only survives there, it thrives. Exploring this realm is incredibly difficult. Darkness alone presents a major challenge. Human beings rely heavily on sight. In total darkness, orientation becomes disorienting. Submarines and robotic vehicles must carry powerful lights, but these lights only illuminate a small area. Beyond that bright circle lies endless blackness. Navigation is also complicated. In shallow water, satellites can help determine position, but deep underwater, signals cannot travel easily. Explorers must rely on sonar and careful measurements. Even with advanced technology, mapping the deep ocean floor remains incomplete. In fact, more of the surface of the Moon and Mars has been mapped in detail than the deepest parts of Earth's oceans. Specialized submersibles have been designed to withstand the intense pressure of the deep. Some are crewed by humans, others are remotely operated vehicles controlled from ships at the surface. These machines must be built with thick, strong materials. Even a small crack could lead to disaster. The engineering required is complex and expensive. The cost of deep-sea exploration is high. Research vessels, equipment, trained crews, and long expeditions require significant funding. Because of these challenges, only a small fraction of the deep ocean has been directly observed. Each expedition often reveals new species and unexpected discoveries. It is common for scientists to encounter organisms that have never been seen before. The darkness also affects communication. Radio waves, which carry signals for phones and many other devices, do not travel well through water. Communication between deep-sea vehicles and the surface must rely on cables or acoustic signals. These methods are slower and less reliable. Despite the difficulties, scientists continue to explore because the deep ocean holds important clues about Earth's history and the nature of life itself. Sediments on the ocean floor contain records of past climates. Studying deep-sea ecosystems helps researchers understand how life adapts to extreme conditions. Some even believe that studying hydrothermal vent communities could provide insights into how life began on Earth. There is also growing interest in deep-sea resources. Minerals such as manganese, cobalt, and rare earth elements can be found on the ocean floor. Some companies are exploring the possibility of deep-sea mining. However, this raises serious environmental concerns. The ecosystems in perpetual darkness are delicate and slow to recover from disturbance. Because life there grows and reproduces slowly, damage could last for generations. The absence of sunlight creates a sense of mystery that captures human imagination. Stories about strange sea monsters and unknown creatures often come from glimpses of deep-sea animals brought to the surface. When sunlight suddenly hits them, their fragile bodies can change or collapse. Colors that might be vibrant under specific wavelengths appear dull. Many deep-sea creatures are red or black, colors that make them nearly invisible in the blue light that sometimes filters down from above. In total darkness, camouflage takes on new meaning. The deep ocean also plays a critical role in regulating the planet. It stores vast amounts of carbon dioxide. It influences global climate patterns. Currents circulate water around the globe, connecting different regions. Even though the deep sea is hidden from view, it is deeply connected to life on land. Psychologically, the idea of eternal darkness is unsettling for many people. Humans evolved in daylight environments. We are comforted by cycles of day and night. In the deep sea, there is no sunrise to mark a new beginning, no seasonal change in light. Time is measured differently. Creatures there may rely on internal biological clocks or subtle environmental cues, but they do not experience the rhythm of sunlight. Studying life without sunlight challenges our assumptions about what is necessary for survival. For a long time, scientists believed that sunlight was essential for complex ecosystems. The discovery of thriving communities around hydrothermal vents changed that belief. It showed that life can exist in places once thought impossible. This has implications beyond Earth. When scientists consider the possibility of life on other planets or moons, they think about environments without sunlight. For example, beneath the icy surface of Jupiter's moon Europa, there may be an ocean kept warm by internal heat. If life can survive in the deep ocean on Earth without sunlight, perhaps it could survive elsewhere under similar conditions. In the deep ocean, sound travels differently than light. Some animals may rely more on vibrations and movement than on vision. Whales communicate using low-frequency sounds that can travel long distances. Even in darkness, sound connects creatures across vast spaces. Every journey into the deep reveals how much remains unknown. Strange fish with transparent heads, squid with glowing arms, creatures with delicate umbrella-like bodies drifting slowly in the dark. Each discovery reminds us that Earth still holds mysteries. Life without sunlight is not a lifeless void. It is a realm shaped by scarcity, pressure, cold, and darkness. It is a place where evolution has taken unusual paths. Bodies glow instead of reflect. Mouths grow larger. Eyes either shrink or expand dramatically. Energy flows from falling debris or from the planet's own chemical heat. Exploration of this environment requires courage, innovation, and patience. It demands machines that can endure crushing pressure and navigate without visual landmarks. It requires scientists willing to spend weeks at sea, studying creatures that may never be seen again. The absence of natural light below 1,000 meters creates one of the most extreme habitats on Earth. Yet it is also one of the most important. It supports unique life forms. It influences global systems. It challenges our understanding of biology. And it reminds us that even in complete darkness, life finds a way to exist. In that endless night, glowing signals flicker. Slow-moving shapes drift silently. The ocean floor stretches outward into blackness. No sunrise will ever touch that world. But it is not empty. It is alive, complex, and deeply connected to the planet above. Perpetual darkness may seem frightening from a human perspective, but for the creatures that call it home, it is simply normal. Their world has never known sunlight, and yet, against all odds, it thrives. The deep ocean is a realm of extreme conditions, a hidden world where sunlight never penetrates and pressures soar to levels that could crush ordinary objects with ease. In this dark expanse, water temperatures linger just above 0 degrees Celsius, creating an environment that is both hostile and fascinating. Despite the absence of warmth, life persists here, adapting in remarkable ways to survive the nearly freezing waters. Understanding these conditions is essential not only for marine biology, but also for human exploration, as the extreme cold shapes everything from the tiniest microscopic organisms to the strategies used by deep-sea explorers. Water near 0 degrees Celsius behaves in ways that are strikingly different from what we experience on the surface. Unlike the air or the relatively warm coastal waters, deep ocean water moves slowly and retains cold temperatures consistently throughout the year. This persistent chill slows chemical reactions and biological processes, making life in the abyss incredibly different from life in shallower, sunlit regions. The very cold environment affects the metabolism of marine animals, the rate at which food is digested, and even the ways that organisms grow and reproduce. Some creatures have evolved proteins and enzymes that remain functional at these low temperatures, essentially rewiring their biology to cope with a world that would freeze most surface animals. Humans venturing into these depths face challenges that are just as extraordinary. Submersibles and deep-sea research vessels must be designed to withstand both the immense pressure and the icy water. Even with advanced technology, prolonged exposure to temperatures barely above freezing can be dangerous, making life support systems, insulation, and thermal regulation critical components for any expedition. Scientists studying the abyss must also contend with the cold's effect on instruments and samples. Equipment can become sluggish, and delicate sensors may behave unpredictably, requiring careful calibration and constant monitoring. The impact of near-freezing temperatures extends to chemical and physical processes in the ocean as well. Cold water holds more dissolved gases than warmer water, meaning that oxygen, carbon dioxide, and other gases can accumulate in surprising concentrations. This makes the deep ocean a critical reservoir for elements that regulate global climate and support life. Currents in these frigid waters move slowly but powerfully, carrying nutrients and influencing ecosystems far from the abyss itself. The way that cold water interacts with salt and pressure also affects density, creating layers that can trap certain organisms while allowing others to drift with the flow. Life in these extreme temperatures often takes forms that are startling to the human imagination. Some fish produce antifreeze proteins that prevent their blood from freezing, while certain crustaceans develop flexible membranes and slow metabolisms that let them survive months without food. Bioluminescence is common, a glowing adaptation that compensates for the absence of sunlight and allows creatures to find prey, communicate, or avoid predators. Microbes thrive in the cold as well, often forming the foundation of complex food chains. These organisms carry out chemical reactions at a pace that is extremely slow by surface standards, yet they sustain entire ecosystems where the energy from sunlight never reaches. The human fascination with these frigid depths is not only scientific, but also historical. For centuries, explorers have imagined the abyss as a mysterious frontier, a place of monsters, lost treasures, and unknown phenomena. Early deep-sea expeditions relied on weighted lines and simple diving bells, and many failed due to the deadly combination of pressure, darkness, and freezing water. Today, technological advances have made it possible to send robotic probes and manned submersibles to the ocean's deepest trenches, yet the near-freezing temperatures still pose a formidable obstacle. Engineers must account for the way metal contracts, lubricants thicken, and batteries lose efficiency in extreme cold. These cold conditions also reveal fascinating insights about Earth's climate system. The deep ocean acts as a slow-moving thermostat, absorbing heat from surface waters and storing it for decades or centuries. Changes in temperature at these depths can have ripple effects across the planet, influencing weather patterns, sea levels, and the distribution of nutrients that sustain fisheries and marine life. Studying how freezing temperatures affect water density and circulation helps scientists understand phenomena like thermohaline circulation, which is critical for distributing heat and maintaining the balance of the global climate. Exploring the abyss requires more than just technology. It demands patience and a deep understanding of the way cold shapes every aspect of life and matter in these waters. Every dive into these near-0-degree zones is a careful negotiation with physics, biology, and human endurance. Researchers must prepare for the possibility that a slight miscalculation can endanger both people and equipment. Yet, despite the risks, the rewards are immense. Each discovery in the cold abyss expands our knowledge of biology, geology, chemistry, and the resilience of life itself. Even the simplest organisms in the cold abyss reveal remarkable adaptations. Some bacteria thrive by metabolizing minerals from rocks or the chemical byproducts of hydrothermal vents, while larger animals like the colossal squid or deep-sea anglerfish have bodies perfectly suited to slow movement and energy conservation. The cold slows decay, allowing the remains of creatures to persist longer than in warmer waters, providing scientists with unique opportunities to study species and ecosystems that would otherwise vanish quickly. These adaptations are not random. They are precise responses to the relentless pressure and freezing temperatures that define the deep ocean. The interplay between cold water and human exploration also highlights the limits of our engineering and ingenuity. Submersibles must be equipped with thermal shields and insulated compartments, and pilots need specialized suits that provide both mobility and protection. Communication with the surface is limited by the density and cold of the water, forcing reliance on pre-programmed missions and autonomous vehicles. Even food, medical supplies, and oxygen must be carefully managed for deep-sea expeditions, as resupply in such a hostile environment is nearly impossible. Every detail matters when operating in a space where a few degrees difference can determine survival. In addition to the biological and technological aspects, the cold abyss plays a crucial role in Earth's chemical cycles. Nutrient transport, gas solubility, and sediment formation all operate under the influence of near-freezing temperatures. Cold water can hold large amounts of oxygen, creating pockets where life thrives even in complete darkness. Similarly, carbon dioxide absorption at these depths contributes to regulating the planet's greenhouse gases, linking the obscure environment of the deep ocean to the survival of life on land. Without these processes, surface ecosystems and climate systems could not function as they do today. Studying these cold environments also informs our understanding of life beyond Earth. Scientists speculate that icy moons like Europa or Enceladus may host oceans with temperatures just above freezing, similar to Earth's abyssal plains. By understanding how organisms survive in our own near-zero-degree oceans, we gain insights into the potential for life in extraterrestrial oceans. The biological and chemical lessons learned from Earth's frozen depths may one day guide missions to explore alien seas, expanding the frontier of science in ways that seem as fantastic as the discoveries of the deep ocean itself. The human fascination with the cold abyss is both practical and philosophical. On one hand, understanding the environment informs conservation efforts, fisheries management, and climate research. On the other hand, it challenges our perceptions of what life can endure. Each new species discovered, each chemical process understood, and each technological breakthrough achieved in the icy waters reveals a world of persistence, adaptation, and resilience. Life persists in conditions that seem inhospitable, and human curiosity pushes the limits of what can be known and explored. Even simple measurements become complex in near-freezing conditions. Instruments that monitor temperature, salinity, and pressure must function precisely despite the cold, while samples collected for study can change quickly if not carefully preserved. Freezing temperatures slow biological processes, which can both help and hinder research. On one hand, slow decay preserves delicate tissues and organisms, offering scientists a rare glimpse into deep-sea life. On the other hand, reactions that normally occur rapidly on the surface may take days or weeks to manifest, requiring researchers to adjust methods and expectations accordingly. The interplay of cold, pressure, and darkness creates a unique stage for life, shaping everything from microbial communities to large predators. Each adaptation, whether chemical, physiological, or behavioral, represents a solution to the challenges posed by near-zero-degree water. Creatures in the abyss live slowly, move efficiently, and rely on scarce resources, demonstrating ingenuity and resilience in the face of environmental extremes. For humans, witnessing these adaptations inspires both awe and respect, highlighting how much we still have to learn about Earth's final frontiers. Deep beneath the surface of the ocean are the toxic hydrothermal vents, natural phenomena that rise from the ocean floor with incredible heat and a chemical composition so extreme that it creates a world utterly alien to life as we usually understand it. These underwater vents are the crucibles of chemical hazards, a place where Earth itself seems to breathe and exhale with both violence and life-giving energy, all at the same time. Hydrothermal vents are formed along the tectonic boundaries of our planet, mostly at the mid-ocean ridges where the Earth's crust is constantly spreading. Here, seawater seeps into cracks in the ocean floor, traveling deep into the Earth's crust. As it descends, it comes into contact with molten rock called magma, which heats the water to extraordinary temperatures. This is not just warm bath water we are talking about. This water can reach nearly 400 degrees Celsius. To put that into perspective, water boils at 100 degrees Celsius at the surface, but because of the extreme pressure thousands of meters below the sea, this water can remain in a liquid state even at temperatures far beyond boiling. Imagine liquid hotter than any water you could safely touch, pushing up from the ocean floor, carrying with it a complex soup of chemicals and dissolved minerals. As this superheated water rises back toward the ocean floor, it emerges from fissures and cracks in the rock, forming what appear to be underwater chimneys. These chimneys, sometimes called black smokers or white smokers depending on the minerals they release, emit plumes of water so dense with chemicals that they look like smoke, though no fire is involved. Black smokers, for instance, are thick with iron sulfide, which gives the plume a dark, almost black appearance. White smokers, in contrast, carry barium, calcium, and silicon, giving their plumes a lighter, ghostly appearance. Both, however, are dangerous, highly toxic, and chemically active, creating an environment that is incredibly hostile to most forms of life. The chemical hazards present in these hydrothermal vents are numerous and complex. Among the most notable are the sulfur compounds. Sulfur in these environments often appears as hydrogen sulfide, a gas that smells of rotten eggs and is extremely poisonous. For most animals, even tiny amounts of hydrogen sulfide can be deadly because it interferes with the body's ability to use oxygen, effectively suffocating cells from the inside. Humans, of course, would find being anywhere near such a vent without specialized equipment to be fatal in minutes. But even beyond hydrogen sulfide, there are countless other compounds: methane, ammonia, carbon dioxide, and heavy metals such as copper, zinc, and arsenic. These chemicals are all dissolved in the vent fluids, creating a cocktail that is as hostile as it is fascinating. In addition to toxicity, the water itself is under enormous pressure. At depths of 2,000 to 4,000 meters or more, the pressure is hundreds of times greater than what humans experience at sea level. This pressure is what allows water to remain liquid at temperatures that would otherwise boil away into steam. But for any creature not adapted to these extremes, both the temperature and the chemical load are lethal. The combination of heat, pressure, and chemical hazards means that hydrothermal vents are some of the most extreme environments on Earth, places that challenge the very definition of habitability. Despite these dangers, hydrothermal vents are not entirely barren. On the contrary, they are among the most productive ecosystems in the deep ocean. The secret lies in a process that defies ordinary life: chemosynthesis. Unlike photosynthesis, which depends on sunlight, chemosynthesis relies on chemical energy. Microbes near the vents consume the toxic chemicals, especially hydrogen sulfide, and convert them into energy, creating the foundation of a food web entirely separate from sunlight. These microbes form dense mats, shimmering under the faint light of submersibles and glowing in some cases with bioluminescence. They are tiny but incredibly resilient, able to survive in water that would kill most life instantly. Around these microbial communities, other creatures thrive, adapted to the chemical hazards. Tube worms, clams, shrimp, and crabs are some of the larger inhabitants of vent ecosystems. Tube worms, for example, can reach lengths of over 2 meters and survive without a mouth or digestive system. Instead, they host symbiotic bacteria inside their bodies, bacteria that convert the vent chemicals into nutrients that the worms can use. Similarly, certain clams and mussels harbor bacteria in their gills, forming a partnership that allows them to withstand the poisonous waters. These adaptations are remarkable examples of life evolving to exist in a world that, at first glance, seems utterly uninhabitable. Hydrothermal vents are not static features. They are dynamic, sometimes violent, and constantly changing. The chemical composition of the vent fluids can vary dramatically over time. An eruption or a shift in the magma below can alter the temperature and chemical content of the vent plumes, sometimes within days or hours. New chimneys can form, old ones collapse, and entire vent communities can disappear or emerge in a matter of years. The hazards are therefore not only constant but unpredictable. For scientists exploring these environments, the risk is ever present. Exposure to toxic chemicals, sudden releases of superheated water, or being caught in a collapse of the fragile vent structures. The toxic nature of the vent chemicals is also of great interest to scientists studying the origins of life. Some theories suggest that life on Earth may have begun in these harsh environments. The chemical richness of the vent fluids, combined with heat and mineral surfaces, could have provided the energy and molecular building blocks for the first organisms. Experiments have shown that amino acids and other essential molecules can form in conditions that mimic hydrothermal vents, suggesting that the chemical hazards that make these vents deadly today may have been crucial for life to start billions of years ago. The study of hydrothermal vents is not only about biology, but also about chemistry and geology. The superheated water dissolves minerals from the rock it passes through, carrying them to the surface. As the water cools, these minerals precipitate, forming the black or white chimneys. Iron, copper, zinc, and even precious metals like gold and silver can be found in these deposits. The vents are therefore natural laboratories for understanding how minerals form in extreme conditions and how chemicals interact under high pressure and temperature. Some researchers even see hydrothermal vents as analogues for environments on other worlds, such as Jupiter's moon Europa or Saturn's moon Enceladus, which may harbour similar underwater hydrothermal activity beneath their icy shells. The hazards associated with hydrothermal vents extend beyond the immediate area of the vent itself. The chemical-rich plumes can spread through the surrounding water, affecting marine life hundreds of meters away. For instance, the heavy metals and sulfides can be toxic to organisms not adapted to vent environments, creating a chemical boundary that most life cannot cross. The pH of vent water is often very low, meaning it is highly acidic, which can corrode tissues and shells. Temperature gradients are extreme, with water near the vent being near boiling and water just a few meters away being close to freezing. This combination of heat shock, chemical toxicity, and pressure makes hydrothermal vents one of the most hazardous natural environments on Earth. Exploring these vents is a remarkable technological challenge. Human divers cannot survive at such depths, so remotely operated vehicles and submersibles are used. These machines must withstand crushing pressure, corrosive chemicals, and intense heat. Their cameras capture images of strange ecosystems, towering chimneys, and plumes of water that seem to glow against the darkness. Sampling devices must be carefully designed to avoid contamination and to preserve the integrity of the chemical environment. Even so, accidents happen, and researchers risk damaging delicate vent structures or exposing themselves to dangerous chemicals. Hydrothermal vents also play a role in global chemical cycles. The chemicals they release, particularly sulfur, iron, and carbon compounds, contribute to the chemistry of the deep ocean. Over time, these chemicals can affect ocean acidity, nutrient availability, and even climate regulation. The vents act as natural reactors, where the Earth's internal heat and minerals are combined with seawater to create new chemical species. This process reminds us that Earth's surface and deep interior are intimately connected, and that the chemical hazards of hydrothermal vents are part of a larger planetary system that affects life far beyond the vents themselves. It is fascinating to consider that these vents, with their toxic waters and deadly plumes, are not just destructive forces but also creators. They support life forms found nowhere else on Earth. They drive chemical transformations essential for ocean health, and they offer clues to the origins of life. The same hydrogen sulfide that can suffocate humans fuels entire ecosystems. The same superheated water that could scald a diver to death creates a habitat for organisms that can survive without sunlight, without oxygen in the traditional sense, and in conditions that seem impossible. The mystery of hydrothermal vents continues to grow. Each new expedition uncovers new species, new chemical processes, and new dangers. Microbes that resist extreme heat and toxic chemicals may hold secrets for medicine, biotechnology, or even space travel. Minerals precipitating from vent chimneys may be harvested in the future, though such activity would have to be carefully balanced with the need to protect these fragile ecosystems. Understanding how life survives, adapts, and thrives in these chemically hostile environments expands our knowledge not only of biology, but also of chemistry, geology, and the resilience of life itself. In conclusion, hydrothermal vents are more than just underwater geological features. They are dynamic, chemical-laden environments that test the limits of what we consider habitable. Their superheated waters, rich with sulfuric compounds and toxic chemicals, create a hostile environment that is lethal to most life but astonishingly supportive for those adapted to it. The vents challenge our understanding of survival, adaptation, and the potential for life in extreme environments, both on Earth and beyond. They are laboratories of natural chemistry, habitats of extraordinary organisms, and windows into the deep processes of our planet. Every plume of water that rises from the ocean floor is a reminder that even in the darkest, hottest, and most toxic corners of the world, life can find a way, and chemistry can tell stories more complex than we ever imagined. Through the lens of these vents, we see Earth not as a static, gentle place, but as a dynamic, sometimes violent, yet incredibly creative planet. The superheated plumes, the black and white chimneys, the clouds of hydrogen sulfide, and the hidden ecosystems all combine to paint a picture of a world at once terrifying and magnificent. To explore hydrothermal vents is to explore the extremes of nature, the heat, the pressure, the chemicals, and the life that somehow endures against all odds. It is a journey into the hidden engine rooms of our planet, where chemistry and biology collide, where danger and wonder coexist, and where the toxic and the life-giving are inseparably intertwined. Even with all that we have discovered, hydrothermal vents remain largely mysterious. Their remote locations, the extreme conditions, and the complexity of their chemical environments mean that every new expedition can reveal surprises. The more we learn, the more we realize how little we truly understand about the deep ocean, the chemistry of life, and the resilience of organisms in extreme environments. In this sense, hydrothermal vents are not just hazards to be feared. They are keys to understanding some of the most fundamental processes that shape life, chemistry, and the Earth itself. The oceans of our planet are vast, stretching farther than the eye can see, and yet even with all the exploration humans have done, much of their depths remain an enigmatic mystery. Among the most haunting and captivating regions are the deep-sea trenches, narrow chasms in the ocean floor that plunge to unimaginable depths. These dark and foreboding places are home to creatures so strange, so unlike anything we are accustomed to on land or even in shallower waters, that they almost seem like beings from a dream or nightmare. Scientists who have dared to explore these zones often describe them as alien worlds, where light barely reaches, and the pressure is so intense it could crush a submarine as easily as a tin can. It is within these extreme conditions that life has adapted in ways that are both terrifying and awe-inspiring. One of the most remarkable examples of adaptation in the deep sea is the giant amphipod, a creature that seems at once fragile and formidable. Amphipods are small crustaceans, similar to tiny shrimp, but in the depths of the trenches, some grow to monstrous proportions, reaching lengths of nearly a foot or more. Imagine a creature the size of a small human forearm scavenging silently along the ocean floor, using its specialized limbs to sift through sediments in search of food. Unlike the vibrant, colorful life forms seen in tropical reefs, these amphipods are often translucent or dark, their bodies designed to withstand crushing pressures that would obliterate ordinary animals. Scientists who have captured footage of them are often struck by their eerie appearance. Their elongated limbs and oversized eyes make them seem like specters of the deep, perfectly suited to a world where sunlight does not penetrate and where every movement must be calculated to conserve energy. Even more chilling are the anglerfish, perhaps the most iconic of deep-sea predators. Their appearance has become a symbol of the ocean's uncanny and nightmarish side, largely because of their grotesque yet strangely fascinating adaptations. These fish possess a bioluminescent lure, a small appendage protruding from their heads which glows in the darkness to attract prey. In a world where light is almost non-existent, this tiny glowing beacon can mean the difference between life and death. The anglerfish's mouth is filled with long, needle-like teeth, angled inward so that once prey enters, there is almost no escape. They can swallow animals almost as large as themselves, an adaptation necessary in an environment where meals are few and far between. Reproduction is just as peculiar. In some species, the male is nothing more than a tiny parasite, fusing to the much larger female for life, surviving entirely on her body. It is a bizarre and macabre arrangement, perfectly illustrating the extreme pressures of survival in a world that is unforgiving in every sense. But for every species that has been discovered, scientists believe there are countless others lurking in the shadows, completely unknown to humanity. Deep-sea exploration is a relatively recent endeavor in the grand timeline of science. Only in the mid-20th century did humans first manage to send submersibles into the deepest trenches, and even now, less than 5% of the world's oceans have been explored. In places like the Mariana Trench, the deepest known part of the ocean, descending nearly 7 miles from the surface, cameras and robotic vehicles reveal glimpses of life that often defy comprehension. There are reports of fish with translucent skin, creatures that float as though weightless, and enormous jellyfish with tendrils longer than school buses. Each expedition seems to uncover something stranger than the last, hinting at a diversity of life forms that may be beyond our current imagination. In these alien landscapes, predation takes on forms that are foreign to our everyday experiences. Some species have developed extreme mechanisms for detecting prey, relying on heat sensors, lateral line systems that sense vibrations, or even electrical fields. Others have evolved to consume almost anything they encounter, as meals can be unpredictable and infrequent. For example, scavengers will feast on the remains of animals that have sunk from the upper layers of the ocean, known as marine snow, which can include everything from tiny plankton to the carcasses of whales. In this context, survival is not about speed or strength alone, but about being perfectly adapted to exploit any opportunity that arises, no matter how rare. The pressure in these environments is another defining factor. At depths of more than 35,000 feet, the weight of the water above is equivalent to over 8 tons per square inch. For creatures living here, ordinary lungs or swim bladders would collapse instantly. Instead, they have developed flexible bodies, cartilaginous skeletons, and proteins that function without being crushed by the immense force. Their biochemistry is extraordinary. Enzymes are tuned to operate at temperatures just above freezing, while their cell membranes remain fluid despite extreme pressure. Life here exists at the edge of possibility, thriving in conditions that would obliterate almost anything else. Yet, despite their resilience, many of these deep-sea creatures remain invisible to us, not just physically, but scientifically. Every expedition yields new mysteries, shapes and movements that do not match any known species, flashes of bioluminescence in patterns that defy categorization, and behaviors that challenge our understanding of evolution. It is entirely possible that some of the largest predators of the deep have yet to be observed, creatures whose existence is only hinted at by the occasional shadow or ripple detected by sonar. These unknown species may be capable of extraordinary feats, from hunting with methods unseen on the surface to surviving without oxygen or consuming energy in ways we cannot yet measure. In this sense, the deep sea is both a biological frontier and a realm of nightmares filled with life forms that feel almost supernatural. Some of the strangest adaptations involve reproduction and survival strategies that are completely alien to surface dwellers. Beyond the anglerfish, other deep-sea species have evolved hermaphroditism, the ability to change sex or to reproduce without a mate, ensuring that even in sparsely populated regions, their species can endure. Certain types of worms and mollusks can survive by consuming chemicals emitted from hydrothermal vents, effectively using energy derived from the Earth itself rather than the Sun. These vents, located along tectonic plate boundaries, create small oases in an otherwise barren landscape where clusters of life thrive in extreme heat and mineral-rich water. Around these vents, life can appear almost surreal. Crabs with transparent shells, clams hosting chemosynthetic bacteria in their gills, and tube worms towering several feet above the ocean floor, all forming a bizarre ecosystem dependent on chemistry instead of light. Bioluminescence is another hallmark of the deep. Far from being merely decorative, the ability to produce light serves multiple critical purposes: luring prey, deterring predators, or communicating with members of the same species. The patterns of light can be complex, ranging from simple glows to intricate flickers that convey information across vast distances. Some creatures even use light to mimic others, confusing predators or ambushing unsuspecting prey. In a realm where darkness reigns supreme, illumination is power, and life has learned to manipulate it with astonishing precision. Temperature plays an equally important role. While the surface of the ocean may experience a wide range of warmth, the deep sea is often just above freezing. Yet some creatures tolerate this cold, moving sluggishly to conserve energy, while others thrive in pockets of heat near vents, where temperatures can reach hundreds of degrees Fahrenheit. This combination of extremes, pressure, cold, scarcity, and occasional bursts of heat, creates one of the harshest habitats on Earth, demanding specialization and resilience in every aspect of life. Despite their extreme conditions, these deep-sea predators and bizarre creatures are part of a delicate and interconnected ecosystem. Many are scavengers, cleaners, or prey for larger predators, forming a complex web of life that is still poorly understood. The loss of even a single species can have unforeseen consequences, not just in the trenches but throughout the oceans. This delicate balance is a reminder that while we have explored the surface of the sea extensively, the deeper layers are still largely unknown and potentially filled with marvels and terrors that we cannot yet comprehend. Exploration continues to uncover astonishing surprises. In recent decades, remotely operated vehicles and deep-diving submarines have captured footage of enormous squid, fish with eyes larger than dinner plates, and previously unknown jellyfish with shapes and structures unlike anything recorded before. Even more astonishing are the glimpses of creatures that appear almost ethereal, floating gracefully in the dark like apparitions, their delicate forms moving with an elegance that belies the harsh conditions of their environment. Scientists have described moments when entire walls of the trench seem to come alive, with life forms clinging to rock faces, moving in patterns that suggest intelligence and coordination, though much of this remains speculative. The unknown predators of the deep are perhaps the most captivating of all. While we have identified species like the anglerfish and giant amphipods, there are hints that far larger and more formidable creatures may exist in the uncharted reaches of the ocean. Sonar anomalies and fleeting shadows suggest the presence of enormous animals, possibly equivalent in size to whales, adapted to live in near-total darkness and under extreme pressure. The idea that vast, unknown predators patrol these abyssal regions is both thrilling and terrifying, raising questions about what else exists in a world we can barely touch. Every expedition has the potential to reveal species never imagined, and with each discovery, the ocean's depths grow even more mysterious. In oceanic trenches, creatures exist that challenge everything we think we know about the limits of life. Among these incredible forms of life are xenophyophores, enormous single-celled organisms that defy what most people understand about cells and the scale at which life can exist. Unlike the microscopic single-celled life we are familiar with, such as bacteria and amoebas, xenophyophores can grow to sizes so large that they can be seen with the naked eye. Some of them stretch for more than 10 centimeters across, forming intricate and fragile structures on the deep sea floor. They look almost like miniature cities, their bodies crisscrossed with chambers and tunnels, trapping particles and debris to build protective shells that provide them with stability in the immense pressure of the deep ocean. These creatures are not just biological curiosities, they are windows into the extraordinary adaptability of life on Earth. In the pitch-black depths of trenches like the Mariana Trench, where water pressure can reach over 1,000 times the pressure at sea level, few living things can survive. Yet xenophyophores thrive there, feeding on tiny particles that drift down from the ocean's surface, called marine snow. They carefully capture and process these particles, using them to sustain their massive singular bodies. Scientists have observed that their structures can create habitats for other deep-sea creatures, acting almost like a coral reef in miniature, providing shelter for worms, small crustaceans, and even some rare fish that venture into these abyssal zones. Their presence hints at an intricate, interconnected ecosystem that exists far from the sun, sustained by particles, minerals, and chemosynthetic processes, rather than sunlight-driven photosynthesis. The sheer size of xenophyophores is one of their most fascinating traits. While most single-celled organisms are invisible without a microscope, these giants blur the line between microscopic life and macroscopic structures. Scientists have speculated on how a single cell could achieve such immense size without succumbing to the limits of diffusion, the process by which nutrients and waste products are exchanged within cells. Unlike ordinary cells, xenophyophores compartmentalize their internal structures, creating multiple nuclei that distribute essential functions throughout their sprawling bodies. This unique cellular organization allows them to maintain metabolic activity across a vast area, demonstrating the extraordinary possibilities of life adapting to extreme and isolated environments. Each specimen is a masterpiece of evolution, a testament to the ability of life to defy conventional rules, adapting to pressures, darkness, and scarcity of food in ways that still baffle scientists today. However, the study of xenophyophores and other deep-sea organisms is not just a matter of marveling at their unusual forms. It is also a journey into the unknown dangers that might lurk in the extreme reaches of the ocean. In these isolated, high-pressure environments, microorganisms have evolved independently for millions of years, separated from the rest of the biosphere by vast distances and unique conditions. The deep trenches are like alien worlds on our own planet, and the life forms within them could carry biological properties completely unfamiliar to humans. Scientists who explore these depths must be careful, because even the simplest-looking microorganism may possess traits capable of causing harm if introduced to life above the deep ocean. These dangers are not theoretical. Researchers have long understood that extremophiles, organisms that thrive in extreme environments such as hydrothermal vents, deep subsurface rocks, or frozen Antarctic lakes, can produce chemicals and compounds that are toxic, highly reactive, or otherwise hazardous to humans and other surface-dwelling life. Some microbes develop enzymes capable of breaking down materials in ways that would be catastrophic if they were ever exposed to ordinary ecosystems. Others may carry unknown viruses or genetic elements that could interact unpredictably with terrestrial life. The biological risks of deep-sea exploration are compounded by our limited knowledge. Despite advances in technology, the vastness of the ocean, and particularly its deepest trenches, means that we have seen only a tiny fraction of what exists there. Every expedition that reaches extreme depths uncovers new species, many of which have no known relatives in any catalogued ecosystems. The discovery of a new microorganism, especially one from depths measured in tens of thousands of feet, is a reminder that life on Earth is not a closed system. In these extreme zones, microbes may operate with entirely different biochemical processes than anything familiar to us. Some may metabolize chemicals that are rare or non-existent at the surface, while others could survive at pressures and temperatures that would instantly destroy ordinary cells. While these adaptations are remarkable from a scientific perspective, they also present an uncertain and potentially dangerous frontier. Researchers must handle such organisms with extreme care in controlled laboratory environments, often using specialized containment procedures to prevent unintended exposure or contamination. In many ways, the deep ocean is not just a place of discovery. It is also a reminder of the delicate balance between curiosity and caution. Xenophyophores themselves, while fascinating and relatively harmless, also illustrate this tension. Their enormous bodies are composed of heavy, mineralized particles that they collect from the ocean floor, a process that can involve absorbing metals and other compounds from their environment. Some studies suggest that these organisms might accumulate substances that could be toxic to other life forms if ingested, although the full implications remain uncertain. More broadly, their habitats may harbor microorganisms that have never interacted with humans or terrestrial animals, meaning that even a small sample of sediment from a trench could carry a previously unknown microbial ecosystem. Such ecosystems might include bacteria capable of surviving extreme heat, cold, acidity, or chemical concentrations that would destroy most life on Earth. These extremophiles are of intense scientific interest, not only for understanding life on Earth, but also for studying the potential for life on other planets, such as the icy moons of Jupiter and Saturn, which may have subsurface oceans with conditions similar to those of our own trenches. Yet, the same qualities that make these organisms fascinating for astrobiology also make them unpredictable. Scientists cannot fully anticipate how these microbes would behave outside their native environment. Historically, the study of extremophiles has yielded both amazing discoveries and cautionary lessons. Organisms found in deep-sea hydrothermal vents, which survive near superheated water spewing from the Earth's crust, have revealed enzymes that can withstand temperatures of more than 100 degrees Celsius, chemical pathways previously thought impossible, and cellular structures that challenge conventional understanding of biology. Similarly, microbes isolated from ancient permafrost or isolated cave systems have been found to survive for tens of thousands of years, retaining metabolic activity even after millennia of dormancy. Each new discovery stretches our understanding of biology, but also raises questions about containment, cross-species interactions, and the unknown risks of releasing such organisms into familiar ecosystems. In some cases, harmless-looking organisms can carry genes that produce toxins or antimicrobial compounds that, if introduced into human or animal populations, could have serious consequences. While these risks are manageable under controlled laboratory conditions, they highlight the importance of caution when studying life forms from extreme environments like the oceanic trenches. The extreme isolation of these deep trenches further amplifies the potential hazards. In these zones, where light does not penetrate and temperatures can hover just above freezing, organisms have been separated from the rest of the biosphere for millions of years. Over such vast spans of time, evolutionary processes have had the freedom to experiment with forms of life and biochemical pathways unknown on the surface. This isolation is part of what makes the discovery of xenophyrophories so striking. They are not only enormous single cells, but they are also part of ecosystems that may include countless microorganisms we have never seen or studied. Each trench is like a natural laboratory, a unique experiment conducted over geological timescales, where evolution has been allowed to unfold without interference. The deep ocean is essentially a repository of life forms that could be entirely novel to science, each carrying its own genetic instructions, metabolic pathways, and potential for interactions that no scientist can fully predict. As humanity pushes further into the deep ocean, exploring these alien worlds with remotely operated vehicles, deep-sea submersibles, and autonomous sensors, the tension between curiosity and caution grows. Scientists are racing to map, sample, and understand these extreme environments, uncovering life forms that challenge preconceptions about size, resilience, and adaptability. At the same time, every sample brought to the surface, every organism removed from its high-pressure, low-temperature home, represents an encounter with the unknown. The process of studying xenophyrophories or other microorganisms from trenches must be handled with meticulous care. Laboratories must simulate the extreme pressures and temperatures these organisms are adapted to, because sudden exposure to normal surface conditions can destroy them, or worse, activate unknown chemical or biological pathways with unpredictable consequences. Researchers follow strict protocols to minimize risk, but the potential for surprises remains. Just as the deep ocean has remained largely untouched for millennia, the organisms within it are not easily understood or controlled, yet the mysteries of the deep are too compelling to resist. Scientists are particularly fascinated by the potential for xenophyrophories and other deep-sea extremophiles to shed light on the fundamental limits of life. How large can a single cell grow before its internal processes fail? How do organisms maintain homeostasis under thousands of times the pressure experienced at the surface? How do these life forms interact with microorganisms that exist in the same environment? Each new discovery provides a glimpse into the astonishing ingenuity of life on Earth. Beyond their scientific interest, these organisms may also hold practical applications. Enzymes from extremophiles have been used in industrial processes, pharmaceuticals, and biotechnology precisely because they function under conditions that would denature ordinary proteins. The xenophyophores' ability to gather minerals from the deep sea floor and create complex, stable structures may even inspire new materials science, engineering techniques, or environmental strategies for deep-sea resource management. Their lessons extend far beyond biology into the realms of technology and human innovation. Nevertheless, alongside promise comes responsibility. The unknown microorganisms associated with deep-sea environments are not simply neutral subjects for study. They are active, living systems with the potential for impact if mishandled. Microbial dangers are not a product of fiction. They are a reminder that Earth's biosphere is interconnected in ways that we do not fully understand. A single, uncontained microorganism, once exposed to a new environment, could reproduce, mutate, and interact in unforeseen ways. This is why scientists advocating for deep-sea exploration often emphasize extreme caution, meticulous containment, and careful observation. Research missions to oceanic trenches must balance the pursuit of knowledge with respect for the delicate ecosystems being studied. recognizing that each trench, each microbe, each xenophyrophore represents a unique, isolated evolutionary experiment that has survived for millennia under conditions humans are only beginning to understand. One of the most dramatic and dangerous features hidden under the ocean's surface is the Oceanic Trench. Among these trenches, some are located in regions of extraordinary geological activity, particularly along what scientists call the Ring of Fire. This is a vast horseshoe-shaped zone encircling much of the Pacific Ocean, where tectonic plates, the enormous slabs of rock that make up the Earth's outer shell, interact in ways that generate frequent and often violent seismic activity. The positioning of trenches along this ring is not accidental. They are the front lines of the planet's restless tectonic behavior, places where the Earth's surface constantly buckles and bends, giving rise to underwater earthquakes, volcanic eruptions, and even tsunamis. When one examines these trenches, it is impossible not to be struck by their scale and depth. Some of them plunge deeper than Mount Everest is tall. In fact, the Mariana Trench, often cited as the deepest known point on Earth, descends nearly 11 kilometers below the ocean surface. This is deeper than the cruising altitude of most airplanes and far beyond the reach of casual divers. Exploring such trenches is no ordinary undertaking. Scientists and explorers must navigate immense water pressure, near complete darkness, and temperatures that can swing dramatically depending on proximity to tectonic activity. Yet while these challenges are daunting, another invisible threat lurks in the form of seismic activity. The Ring of Fire itself is a region of astonishing energy. It traces the edges of the Pacific Plate and encompasses areas off the coasts of countries such as Japan, Indonesia, the Philippines, New Zealand, Chile, and the western coastline of North America. Within this zone, the Earth's crust is constantly moving. Tectonic plates collide, slide past one another, or sink beneath adjacent plates in a process called subduction. This subduction is particularly important for trenches. When one plate is forced downward beneath another, it creates enormous stress at the boundary. Over time, the stress builds until it is released suddenly, resulting in an earthquake. These underwater earthquakes can vary in intensity from minor tremors that barely register on instruments to cataclysmic events that trigger massive tsunamis capable of crossing entire oceans. For explorers venturing into these deep trenches, understanding the risk of seismic events is not just a matter of curiosity, it is a matter of survival. Unlike earthquakes on land, which might provide some visible warnings such as ground shaking or the sound of collapsing structures, underwater earthquakes are nearly invisible until the effects are felt. Seismic waves travel differently through water and rock, and in the deep ocean there are no natural barriers to slow or stop them. A sudden tremor can destabilize underwater equipment, rupture deep-sea submersibles, or even trigger landslides along the trench walls, creating cascading dangers that are difficult to predict. In some cases, the sudden movement of large masses of sediment and rock can produce a secondary wave, further compounding the peril for scientists and explorers who might be studying marine life, geological formations, or even searching for new species at the ocean's depths. The history of the Ring of Fire is punctuated by numerous devastating seismic events, both on land and underwater. For instance, the earthquake off the coast of Chile in 1960, one of the most powerful earthquakes ever recorded, triggered a tsunami that traveled across the Pacific, affecting distant shores thousands of kilometers away. Similarly, in 1964, Alaska experienced a massive quake that caused extensive damage and also generated tsunami waves that reached as far as Hawaii and the west coast of the United States. In addition to the immediate danger posed by underwater earthquakes, there are long-term implications for those who study the trenches. Repeated seismic activity reshapes the ocean floor continuously. Walls of trenches can collapse, underwater landslides can bury exploration equipment, and volcanic activity can create sudden new hazards. Many of the trenches along the Ring of Fire are also situated near deep-sea volcanoes. These volcanoes may remain dormant for decades, only to erupt with little warning, sending ash, molten rock, and superheated water into the surrounding ocean. The combination of volcanic eruptions and earthquakes can generate powerful underwater shockwaves that ripple through the ocean, affecting marine ecosystems and posing serious risks to human explorers. Modern technology has provided scientists with better tools to study these phenomena, but it has also revealed just how unpredictable the deep sea can be. High-tech submersibles, remotely operated vehicles, and sophisticated sonar mapping systems allow researchers to observe the seafloor in unprecedented detail. Yet, even with these advancements, predicting precisely when and where a seismic event might occur remains a significant challenge. Data collected from seismic monitoring stations, both on land and underwater, can provide warnings of increased activity, but the timing, intensity, and specific location of an underwater earthquake often remain uncertain until it happens. This uncertainty adds an additional layer of tension and caution for anyone venturing into these remote and dangerous regions. Furthermore, the effects of underwater seismic activity extend beyond immediate physical danger. Earthquakes and associated phenomena such as tsunamis can drastically alter the landscape of the ocean floor, disrupting habitats and ecosystems that have existed for millions of years. Deep-sea creatures, many of which are uniquely adapted to life under extreme pressure and near total darkness, can be displaced, buried, or killed by sudden shifts in sediment and rock. For marine biologists and ecologists, this adds another dimension of complexity to the study of deep trenches. Each seismic event is not just a geological occurrence, it is also a significant ecological event, reshaping the environment in which life at these depths must survive. The sheer scale of the energy involved in these events is staggering. Even moderate underwater earthquakes release more energy than most human-made explosions. To put it into perspective, a magnitude 7 earthquake releases roughly 32 times more energy than a magnitude 6 earthquake. When such events occur beneath the ocean, the energy does not remain confined. It transfers through the water, sometimes causing devastating waves that reach coastal areas far removed from the original quake. This understanding underscores why exploration missions in these trenches must always include careful monitoring of seismic activity and comprehensive emergency planning. One cannot discuss trenches along the Ring of Fire without considering the role of human curiosity and ambition. The allure of these underwater chasms is irresistible to scientists, adventurers, and engineers. They promise new discoveries, unknown species, rare minerals, and insights into the Earth's geological history. Yet the very factors that make these locations fascinating, their depth, isolation, and geological volatility, also make them extraordinarily dangerous. Each expedition must balance the desire for knowledge with the reality of the environment, where a sudden earthquake could endanger lives and equipment within moments. Training for such missions is rigorous. Teams of researchers and explorers spend months or even years preparing for deep-sea expeditions. They learn to operate submersibles, navigate the treacherous undercurrents of the trench, and respond to emergency situations. Contingency plans are detailed and rehearsed repeatedly, from rapid ascent procedures to communication protocols with surface vessels. Even with the best preparation, however, the unpredictable nature of seismic activity always introduces a level of risk that cannot be eliminated entirely. In many ways, this tension is part of what makes deep-sea exploration so compelling. It is a confrontation with one of the Earth's most primal and powerful forces. Recent scientific studies have shed new light on the specific risks associated with trenches along the Ring of Fire. By deploying arrays of seismometers and pressure sensors along the ocean floor, researchers can detect minute movements and vibrations that may precede larger seismic events. These data are invaluable in constructing models that attempt to forecast earthquakes, although the science remains imperfect. The deep ocean is an environment where even slight inaccuracies in prediction can have serious consequences, and the scale of these trenches makes it challenging to cover every critical area with monitoring equipment. Nevertheless, each study contributes to a better understanding of the forces at work beneath the waves. The human fascination with the Ring of Fire and its trenches is not limited to science. These regions have captured the imagination of storytellers, filmmakers, and explorers for decades. Tales of monstrous underwater creatures, lost cities, and uncharted geological features abound, inspired by the very real dangers posed by seismic activity and the extreme environments of the trenches. While these stories are often embellished, they echo a fundamental truth. The ocean floor along the Ring of Fire is a place where human ingenuity and courage are tested to the limits, where nature operates on a scale that can be awe-inspiring, terrifying, and humbling all at once. Understanding seismic activity in underwater trenches is crucial for multiple reasons. It informs the design of submersibles and other exploration technology, helps predict and mitigate the impact of tsunamis on coastal populations, and enhances our understanding of the Earth's dynamic processes. Each tremor, each quake, each shift in the ocean floor is a message from the planet itself, a reminder that the Earth is far from static and that beneath the calm surface of the oceans, a world of immense power and complexity is constantly at work. Explorers and scientists venturing into these regions must respect that power, study it carefully, and prepare for the unexpected. While we often imagine the ocean floor as a quiet and still place, it is far from peaceful. Beneath the waves, an invisible and relentless force continuously reshapes the seabed. One of the most dangerous phenomena that lurks in this hidden world is the underwater landslide, sometimes called a submarine landslide, along with massive underwater avalanches of sediment. These events, though invisible from the surface, are among the most powerful natural forces on Earth, capable of unleashing devastation that few humans ever witness, but that scientists study with great care because of their potential to destroy expensive equipment, research submersibles, and even endanger human lives. An underwater landslide is essentially the oceanic equivalent of the giant mudslides or rock slides we sometimes see on steep mountainsides. Instead of soil, rocks, and debris sliding down a mountainside under gravity, these slides involve huge amounts of sand, silt, and other sediments on the ocean floor suddenly shifting and rushing downward. The scale of these slides can be staggering. Some underwater landslides can extend for tens or even hundreds of kilometers, and they may move at astonishing speeds, sometimes exceeding 20 meters per second, which is roughly 72 kilometers per hour. For comparison, that is faster than most cars on a highway. Yet imagine that velocity combined with the immense weight of millions of tons of sand and rock submerged in water. What triggers these underwater landslides is a combination of geological and environmental factors. One of the most common causes is an earthquake. Just as earthquakes can shake buildings on land, the vibrations caused by seismic activity can destabilize sediments resting on steep slopes underwater. These sediments often accumulate gradually over thousands or even millions of years, forming layers that may appear solid but are in fact unstable. When an earthquake occurs, the vibrations can act like a sudden shove, causing entire layers of sediment to give way. Sometimes, even a relatively small tremor is enough to trigger a catastrophic slide if the sediments are particularly unstable or saturated with water. The results are often terrifying in both their suddenness and their sheer destructive power. Underwater avalanches are a closely related phenomenon. While landslides typically refer to the initial detachment and downward movement of sediments, an avalanche refers to the ongoing rush of material once the slide begins. Think of it like a snow avalanche on a mountain. The first block of snow starts sliding, and as it moves, it gathers more snow, accelerating and gaining strength as it goes. Similarly, underwater avalanches start with an initial movement of sediment, but as the material slides down the slope, it picks up more debris, water, and rock, creating a fast-moving, destructive flow that can flatten the seabed and engulf anything in its path. The scale of these underwater events is often unimaginable. Some of the largest documented submarine landslides have involved billions of cubic meters of sediment, covering areas larger than many cities. For instance, research has shown that in certain regions of the Atlantic and Pacific Oceans, underwater slides can extend for hundreds of kilometers from the continental shelf to the deep ocean floor. The pressure and force generated by these moving masses of sediment are enormous. Any object caught in the path, whether a research submersible exploring the deep ocean or an underwater cable carrying electricity or internet signals, faces near certain destruction. The impact is often so sudden that there is little to no time for escape, and even state-of-the-art robotic equipment designed for deep-sea exploration can be crushed, buried, or swept away. What makes these phenomena particularly dangerous is the unpredictability. Unlike a mountain landslide, which may show visible signs like cracks in the soil or tilted trees, underwater sediment flows leave no warning visible from the surface. Oceanographers rely on sonar mapping, sediment sampling, and historical data to identify areas at risk, but the exact timing of a slide is nearly impossible to predict. Sometimes these events can be set off by a combination of seemingly minor factors: a distant earthquake, changes in water temperature or salinity, or even the natural settling and compacting of sediments over time. This combination of stealth, power, and suddenness makes underwater landslides and avalanches one of the most feared threats in deep-sea research. One of the most significant dangers posed by underwater landslides is to submersibles, the specialized vehicles designed to explore the ocean's deepest regions. Manned submersibles, which carry human operators into the extreme pressures of the deep sea, are particularly vulnerable. These vehicles are engineered to withstand incredible pressure, sometimes over 1,000 times that at the surface, yet they are not invincible. An avalanche of sediment moving at high speed can easily crush a submersible or bury it entirely beneath layers of sand and rock. Robotic submersibles face similar threats. Even if they are equipped with powerful thrusters and reinforced hulls, the sheer weight and speed of a sediment avalanche can overwhelm any mechanical system. For engineers and scientists, the prospect of losing a multi-million-dollar submersible in an instant is a real and ever-present risk. Beyond the immediate danger to submersibles, underwater landslides have broader implications for human technology and infrastructure. One striking example is the network of undersea cables that carry the majority of the world's internet and telecommunications traffic. These cables stretch for thousands of kilometers across the ocean floor, linking continents and enabling the global flow of information. An underwater landslide can sever these cables, causing widespread communication outages, financial disruption, and even interruptions in essential services. Historical data shows that landslides triggered by earthquakes or rapid sediment movement have caused major cable breaks, leading to days or even weeks of disrupted connectivity in affected regions. Considering how much the modern world relies on these undersea networks, the importance of understanding and mitigating the risks of underwater landslides cannot be overstated. Scientists study these events with painstaking care. They deploy arrays of sensors, sonar mapping devices, and remotely operated vehicles to monitor the seabed and track changes over time. Sediment cores collected by specialized drilling equipment allow researchers to analyze layers of accumulated material, studying their composition, density, and stability. By understanding the conditions that make underwater slopes prone to sliding, scientists hope to predict areas of risk and develop strategies to protect both human life and technology. These studies often involve interdisciplinary expertise, drawing on geology, oceanography, engineering, and physics. Despite these efforts, the ocean remains a largely unpredictable environment, and even the most sophisticated models can only estimate probabilities, not guarantee safety. One particularly fascinating aspect of underwater landslides is their role in shaping the ocean floor over geological time. While dangerous, these events are a natural and necessary part of the Earth's processes. Sediment flows transport material from shallow coastal areas to the deep ocean, helping to build and reshape underwater canyons and plains. Some scientists even study ancient submarine landslides to understand the history of earthquakes, climate change, and sedimentation patterns. By examining the layers of material deposited by past slides, researchers can reconstruct events that occurred millions of years ago, giving insight into the dynamic and ever-changing nature of our planet. Earthquakes remain the most common trigger, but other factors also play a significant role. Storms and hurricanes, for example, can stir up coastal sediments and deposit them on underwater slopes, increasing the risk of future slides. Volcanic activity beneath the sea can destabilize sediments, while rapid sediment deposition from rivers can overload underwater slopes, creating conditions ripe for a sudden collapse. Even human activity, such as deep-sea mining or the construction of offshore structures, has the potential to destabilize sediments and increase the risk of landslides. In every case, the common factor is a sudden release of stored energy, unleashing a torrent of material that moves with incredible speed and force. The consequences of these slides can extend far beyond the immediate vicinity. Underwater landslides can generate tsunamis, waves so large and powerful that they can cross entire oceans. Historical records show that some of the deadliest tsunamis in history were caused not by surface earthquakes alone, but by underwater landslides triggered by seismic activity. The 1929 Grand Banks earthquake off the coast of Newfoundland, for example, generated a submarine landslide that produced a tsunami reaching the nearby coast, destroying homes and taking lives. These cascading effects highlight the interconnectedness of natural processes and the need for careful monitoring and preparedness. For deep-sea researchers, the risk of underwater landslides is more than a theoretical concern. Every mission to the deep ocean carries inherent dangers, from crushing pressure to mechanical failure, but the unpredictability of sediment flows adds a layer of tension and urgency. Mission planners must carefully consider the topography of the ocean floor, historical seismic activity, and sediment stability before sending submersibles into high-risk areas. Real-time monitoring and emergency protocols are crucial, but even with the best planning, there is always an element of uncertainty. The human fascination with these events is not surprising. There is something both terrifying and awe-inspiring about the idea of millions of tons of material moving silently through the darkness, reshaping the ocean floor in an instant. Documentaries and scientific expeditions often capture the imagination by showing the power of the ocean in ways that are both beautiful and frightening. Efforts to predict and mitigate these events continue to advance. Sophisticated computer models simulate the behavior of sediments under various conditions, from minor tremors to massive earthquakes. Sonar imaging and seismic surveys allow scientists to map the contours and composition of underwater slopes with increasing precision. In some cases, early warning systems have been developed to detect shifts in sediment or underwater tremors that could indicate an impending slide. While no system can prevent a landslide from occurring, these measures can provide crucial time for vessels or submersibles in the area to move to safety. One of the most important lessons from studying underwater landslides is the importance of respect for the ocean's power. The deep sea may seem calm from the surface, but it is a dynamic, ever-changing environment where catastrophic events can occur without warning. The same forces that build the continental shelf and carry nutrients to the deep ocean are capable of destroying even the most advanced human technology. By understanding these processes, scientists not only protect valuable equipment and human lives, but also gain a deeper appreciation for the complex and interconnected systems that govern our planet. In recent years, interest in exploring the deep ocean has surged. From private companies seeking to map the seafloor to governments investing in submarine research for scientific and strategic purposes, the demand for deep-sea exploration has never been higher. This renewed focus makes understanding underwater landslides more critical than ever. Modern submersibles, whether manned or robotic, are designed with advanced safety features, including reinforced hulls, rapid ascent capabilities, and real-time communication with surface teams. Nevertheless, the ocean's unpredictable nature means that even these precautions cannot eliminate risk entirely. Each descent into the depths is a careful balance between curiosity, courage, and respect for the environment. The sheer scale of potential damage caused by submarine landslides is staggering. For researchers working on the ocean floor, even minor sediment shifts can disrupt experiments, damage sensitive instruments, or bury important samples. For infrastructure such as undersea pipelines and communication cables, landslides can cause costly and time-consuming repairs, sometimes cutting off critical services for extended periods. The broader implications extend to coastal communities, where landslide-triggered tsunamis can result in human casualties, economic loss, and environmental destruction. The ripple effects of these events highlight the interconnectedness of human society and natural processes, emphasizing that the ocean is not a distant or isolated environment, but a vital part of our world that commands both caution and respect. One of the most fascinating aspects of underwater landslides is their hidden complexity. Unlike terrestrial landslides, which are often visible and studied after the fact, submarine slides occur in darkness and under immense pressure. Scientists must rely on indirect evidence such as changes in sediment layers, sonar imaging, and seafloor mapping to reconstruct events. Some studies have revealed slides that traveled for hundreds of kilometers, crossing entire continental slopes, with thicknesses reaching hundreds of meters. The energy released in these events is difficult to imagine, equivalent to the explosive force of multiple nuclear bombs. Yet these occurrences are entirely natural, part of the ongoing processes that shape the Earth beneath the oceans. The study of underwater landslides also provides insight into other scientific questions, such as climate change and sediment transport. By analyzing the composition of sediments deposited by past slides, researchers can infer historical ocean temperatures, sediment sources, and even patterns of glacial melting. These insights are valuable not only for understanding the dynamics of the deep ocean, but also for reconstructing the history of the Earth itself. In this sense, the destructive power of submarine landslides is also a source of knowledge, revealing hidden stories written in layers of sand and rock beneath the waves. Despite all the research, the deep sea remains one of the least explored and most mysterious parts of our planet. Every expedition carries the potential for discovery, but also the risk of encountering a sudden, powerful underwater landslide. Bioluminescence, the ability to produce light within one's body, is a common feature in deep-sea life. For creatures dwelling thousands of meters beneath the ocean's surface, light is both a tool and a weapon. Unlike the sunlit world above, where vision is effortless, the deep sea is an inky void. Here, bioluminescence serves multiple purposes, attracting prey, deterring predators, communicating with potential mates, and even camouflage. One of the most striking examples is the use of bioluminescence as a lure. Predators have evolved body parts that glow in the darkness, carefully mimicking the appearance of smaller, harmless creatures. The glow acts like a living fishing lure, enticing unsuspecting prey to swim closer, only to fall victim to a sudden, lightning-fast strike. One of the most famous masters of this deadly light show is the anglerfish. Deep in the Atlantic Ocean, at depths that can exceed several thousand meters, the female anglerfish dangles a long, flexible stalk tipped with a luminous organ called an esker. The light is not produced by the fish itself, but by symbiotic bacteria that live within this organ, glowing with a cold, eerie light. From the darkness, This tiny beacon looks remarkably like a small wriggling organism. Small fish and other creatures drawn to the glow approach, thinking they have found an easy meal. In a fraction of a second, the anglerfish opens its cavernous jaws, revealing rows of sharp, translucent teeth, and swallows its prey whole. The anglerfish's hunting method is the perfect combination of patience, deception, and efficiency, showcasing how bioluminescence can turn a predator into a master of ambush. But the anglerfish is only the beginning. Across the trench environments of the Pacific and Atlantic Oceans, entire ecosystems revolve around light in the darkness. Other deep-sea species, such as certain squids and small crustaceans, have evolved glowing appendages or patches of luminescent skin. These adaptations allow them to lure prey or to attract mates in an environment where conventional communication is impossible. Some species have even taken it further, evolving complex patterns of flashing or pulsating light, essentially creating a visual language that can be used to deceive, mesmerize, or hypnotize. A curious combination of art and survival, this luminescent communication highlights the extreme ingenuity of life in darkness. Ambush hunting is another strategy that thrives in the deep sea, particularly among apex predators. In the trench zones, energy is scarce and prey can be few and far between. The creatures that inhabit these depths must conserve energy while maximizing their chances of survival. Unlike predators that actively chase their prey, ambush hunters employ stealth, patience, and camouflage. They remain motionless for hours or even days, blending perfectly into the shadows and contours of the ocean floor, waiting for a moment of opportunity. When prey comes near, the strike is sudden, precise, and fatal. The combination of bioluminescence and ambush tactics produces some of the most extraordinary predators in the deep ocean. Some species of dragonfish, for example, have rows of tiny, sharp teeth and long, slender bodies designed for rapid, lunging attacks. They possess bioluminescent photophores along their undersides, emitting a dim, ghostly light that camouflages them from below against the faint light from the surface, a strategy called counter-illumination. At the same time, their mouths, jaws, and sometimes a lure at the front of their bodies glow with an inviting brilliance to draw in unsuspecting prey. In this way, they can remain virtually invisible while simultaneously enticing their next meal into a deadly trap. Such predators perfectly illustrate the brutal efficiency of life at these extreme depths, where every adaptation is a matter of survival. Some of the most terrifying ambush hunters in the trenches are giant amphipods, eel-like creatures, and species of hagfish. While many of these creatures appear slow or primitive at first glance, they possess incredible sensory adaptations. Without sunlight, the ocean's inhabitants rely on highly specialized organs to detect vibrations, pressure changes, or faint flashes of light. A predator may sense the slight movement of a distant shrimp or the flicker of a tiny bioluminescent organism, and in response, it can strike with terrifying speed. In these dark, cold waters, the line between predator and prey is razor thin, and the ability to remain unseen and strike with precision is the ultimate advantage. The dangers posed by apex predators in the trench environment are profound, not only for their prey, but also for researchers who venture into these depths. Human technology, such as submersibles and remote-operated vehicles, has allowed scientists to observe these creatures in action, but the extreme pressure, darkness, and sheer unpredictability of the ecosystem make exploration challenging and hazardous. One cannot simply descend to these depths without specialized equipment capable of withstanding pressures hundreds of times greater than atmospheric pressure at the surface. Even then, the act of approaching these creatures can provoke defensive behaviors. Many apex predators are equipped with strong, sharp teeth, crushing claws, or barbed appendages capable of inflicting serious damage. They exist in an environment where only the most efficient and lethal adaptations survive, and they treat any intruder as potential competition or prey. Life in these extreme environments is also a delicate balance. Bioluminescent predators rely on the presence of prey, which in turn depends on the detritus and organic material falling from above, often called marine snow. This constant cascade of nutrients from the surface fuels the deep-sea ecosystem, creating pockets of energy in an otherwise barren world. Ambush hunters must carefully time their strikes and choose locations with sufficient food availability. A failed strike can mean long periods without nourishment, which could be fatal in a world where energy is a precious commodity. The evolutionary pressures in such extreme conditions have produced adaptations and hunting strategies so specialized that even small mistakes can have severe consequences. The diversity of bioluminescent predators is astonishing. Some use their glow passively, merely attracting prey toward them, while others employ sophisticated mechanisms to actively manipulate the behavior of other creatures. Certain species of deep-sea shrimp, for example, possess tiny lights on their tails that they can wiggle to mimic the movement of smaller plankton. Predatory fish, drawn by curiosity or hunger, approach, only to be caught in a precise, sudden strike. This combination of mimicry, deception, and ambush demonstrates the complexity of life in the deep ocean and the incredible evolutionary ingenuity required to survive in such an unforgiving environment. Bioluminescence also plays a defensive role. Many deep-sea organisms are both predator and prey. Squid, jellyfish, and even some deep-sea fish can release clouds of glowing material to distract or confuse predators, allowing them to escape. This bioluminescent smoke screen can dazzle and disorient attackers, giving the smaller or weaker animal a chance to flee. Every light has a purpose, and every flash can mean the difference between life and death. The trench ecosystems are not only fascinating but also crucial for understanding the limits of life on Earth. These zones represent one of the most extreme habitats, and the creatures living there have evolved some of the most sophisticated hunting and survival strategies ever observed. Scientists study bioluminescent predators and ambush hunters to learn not only about biology and evolution, but also about potential applications in technology, medicine, and robotics. The chemical reactions that produce light in these creatures inspire new ways of creating energy-efficient lighting, medical imaging techniques, and even materials that change properties in response to stimuli. In addition to their biological and technological significance, these predators provide insight into the interconnectedness of ocean ecosystems. The actions of a single apex predator can influence entire food webs. By preying on certain species, they help control populations, which in turn affects the distribution of smaller organisms and the cycling of nutrients. Understanding these dynamics is critical, particularly as human activity increasingly impacts even the most remote parts of the oceans. Pollution, climate change, and deep-sea mining have the potential to disrupt these fragile communities, with consequences that ripple far beyond the depths. The ocean has always felt like the last untouched place on Earth, a vast blue world so deep and so wide that it seemed beyond the reach of human hands. For centuries, people believed that no matter what happened on land, the deepest parts of the sea would remain pure, hidden, and protected by distance and pressure. The darkest trenches, the coldest waters, and the most remote valleys of the ocean floor were imagined as silent kingdoms, too far away for human mistakes to reach. But in recent years, explorers and scientists have made discoveries that shattered this comforting belief. Even in the deepest waters ever measured, in places deeper than Mount Everest is tall, they have found signs of us. Not ships, not cities, not living people, but our waste. One of the most shocking examples comes from the deepest part of the ocean, the Mariana Trench in the western Pacific Ocean. This enormous underwater canyon stretches for thousands of miles and plunges down to a depth of nearly 11 kilometers at its lowest point, a place known as the Challenger Deep. For a long time, scientists thought that if there was anywhere on Earth safe from pollution, it would be there. After all, it lies thousands of meters below the surface, in complete darkness, under crushing pressure that would flatten most objects instantly. But when deep-sea submersibles descended into that black water, they did not find untouched purity. Instead, they found plastic. Microplastics, tiny fragments of plastic smaller than a grain of rice, have been discovered in sediments taken from the bottom of the trench. These pieces often come from larger plastic items that break apart over time. Bottles, fishing nets, packaging, synthetic clothing fibers, and countless other everyday products slowly crumble into smaller and smaller bits. Carried by wind and rain, washed into rivers and swept out to sea, these fragments travel across oceans. Some float for years, others sink, and some drift down slowly, like a strange kind of snowfall, until they reach the deepest seabed. Imagine standing at the bottom of the world's deepest canyon and finding pieces of shopping bags and plastic fibers in the mud. It is almost impossible to picture, yet that is exactly what researchers have reported. When scientists collected samples of mud from the deepest parts of the Mariana Trench, they discovered plastic particles embedded in the sediment. These were not rare or isolated finds. In many samples, microplastics were present in surprising amounts, showing that even the most remote ocean depths are connected to human activity. The journey of these pollutants is both complex and tragic. On land, plastic waste often ends up in open dumps, rivers, or coastal areas. From there, it moves into the sea. Ocean currents then carry it across vast distances. Some plastic stays near the surface and gathers in large, swirling patches, like the infamous garbage accumulation in the Pacific Ocean. But much of it does not remain visible. Over time, sunlight and waves break it down into smaller pieces. Marine animals mistake it for food and swallow it. When these animals die, their bodies sink, carrying plastic with them into deeper waters. Even tiny organisms such as plankton can ingest microplastics. When they die, they too sink, adding to a steady rain of plastic debris falling through the water column. This process is sometimes called marine snow, but unlike natural marine snow, which consists of organic material, this new snowfall contains synthetic fragments that nature does not know how to break down easily. The ocean floor becomes a final resting place for much of our waste. And because the deep ocean currents move slowly, sometimes taking hundreds or even thousands of years to circulate, pollutants that settle there can remain for an extremely long time. Plastic is only part of the story. Scientists have also detected toxic chemicals in deep-sea creatures. In some cases, amphipods, small shrimp-like animals living in trenches, have been found to contain high levels of persistent organic pollutants. These chemicals were once widely used in industry and agriculture. Some were banned decades ago in countries around the world, yet they continue to exist in the environment because they do not break down easily. Instead, they travel through air and water, spreading far from where they were originally released. These chemicals include substances that were once used in electrical equipment, flame retardants, and pesticides. Even though many of them were restricted after scientists discovered their harmful effects, they remain present in soil and water. Over time, they enter rivers and eventually reach the sea. Once in the ocean, they attach themselves to particles and are carried downward. Deep-sea animals, which often feed on whatever organic matter drifts down from above, ingest these contaminated particles. What makes this even more disturbing is the process known as bioaccumulation. When a small organism consumes a tiny amount of a toxic chemical, that chemical stays in its body. When a larger animal eats many of those smaller organisms, the chemical builds up in its tissues. As the food chain continues, top predators can end up with very high concentrations of pollutants. This process does not stop in shallow waters. It continues all the way down to the deepest trenches. Animals living thousands of meters below the surface, far removed from human sight, are carrying the chemical fingerprints of industrial society. In one study, scientists were stunned to find that amphipods collected from trenches had levels of certain pollutants that were comparable to, or even higher than, those found in some of the most polluted rivers on Earth. This means that creatures living in one of the most isolated environments on the planet are as contaminated as animals living near major industrial centers. It challenges the idea that distance equals safety. Another alarming discovery involves radioactive materials. In the middle of the 20th century, nuclear weapons testing released radioactive particles into the atmosphere. These particles eventually settled onto land and into the ocean. Nuclear accidents, such as the disaster at Fukushima Daiichi nuclear power plant in Japan, have also contributed to radioactive contamination in marine environments. Although much of this radiation is diluted by the vastness of the ocean, traces of radioactive isotopes have been found in deep-sea sediments. These radioactive particles attach to organic matter and sink. Just like microplastics and toxic chemicals, they travel downward through the water column. Once they reach the ocean floor, they can remain trapped in sediments for long periods. Deep-sea organisms that live in or on these sediments may come into contact with these materials. The problem is not limited to a single trench or a single ocean. In the Pacific Ocean, the Atlantic Ocean, and even the Arctic Ocean, researchers have found microplastics in deep waters and sediments. Ice cores from polar regions have revealed tiny plastic fibers trapped in frozen layers. This means that pollution is not just sinking, it is spreading everywhere. One of the most troubling aspects of deep-sea pollution is how little we truly understand about the ecosystems being affected. The deep ocean remains one of the least explored regions on the planet. More people have walked on the surface of the moon than have visited the deepest parts of the ocean. Many species that live in trenches and abyssal plains have not even been named yet. Some may have lifespans of decades or longer. Others may reproduce very slowly. This means they could be especially vulnerable to environmental changes. When pollutants enter these systems, they may cause harm in ways that are difficult to detect. Toxic chemicals can interfere with reproduction, growth, and behavior. Microplastics can block digestive systems or create a false sense of fullness, leading animals to starve. Even if the plastic itself is not immediately deadly, it can carry other harmful substances on its surface. Plastic acts like a sponge, attracting and concentrating chemicals from the surrounding water. When an animal eats the plastic, it may also absorb these chemicals. There is also the concern that deep-sea pollution could eventually circle back to affect humans. The ocean is not divided into separate, isolated compartments. It is one connected system. Water moves through currents that travel around the globe. Nutrients and materials cycle between deep and shallow waters. Fish and other marine animals migrate across great distances. Some species that feed in deep waters are later caught for human consumption. If these animals carry pollutants in their tissues, those substances could enter the human food chain. The discovery of pollution in the deepest waters has changed the way scientists think about the ocean. It is no longer possible to imagine a truly untouched refuge. Instead, the ocean must be understood as part of a global network shaped by human actions. Every plastic bag thrown away carelessly, every chemical released into a river, and every industrial accident leaves a mark that can travel farther than anyone expects. The technology used to uncover these truths has advanced rapidly. Deep-sea submersibles equipped with robotic arms and high-resolution cameras have allowed researchers to collect samples from extreme depths. Sediment cores reveal layers of history, much like tree rings. By studying these layers, scientists can see when certain pollutants first appeared and how their levels have changed over time. In some cores, the increase in microplastics corresponds with the rapid rise in global plastic production during the second half of the 20th century. The story told by these sediments is not subtle. It shows a clear link between human industrial growth and deep-sea contamination. As plastic production expanded worldwide, so did the amount of plastic reaching the ocean. As chemical manufacturing increased, so did the spread of persistent pollutants. Even actions taken decades ago continue to have consequences today. It is important to understand that the deep ocean is not empty or lifeless. It is filled with strange and remarkable creatures adapted to extreme conditions. Giant amphipods, delicate sea cucumbers, glowing jellyfish, and fish with transparent heads all inhabit this world of darkness and pressure. Many of these animals rely on a delicate balance of chemical signals and environmental stability. Introducing foreign materials into this environment can disrupt that balance. For example, some deep-sea organisms use smell and taste to locate food. Microplastics coated with organic material can release scents that attract animals. When they consume these particles, they may not receive any real nutrition. Over time, repeated ingestion could weaken their health. Scientists are still studying these effects, but early findings suggest that plastic is not just an eyesore. It is an active participant in the ecosystem, often in harmful ways. There is also growing concern about deep-sea mining. As companies look to the ocean floor for valuable minerals used in electronics and renewable energy technologies, they may disturb sediments that have trapped pollutants for decades. If these sediments are stirred up, trapped chemicals and microplastics could be released back into the water, spreading contamination even further. This raises difficult questions about how to balance the demand for resources with the need to protect fragile environments. Public awareness of ocean pollution has grown significantly in recent years. Images of sea turtles tangled in nets and beaches covered in trash have sparked global movements to reduce plastic use. However, the pollution hidden in the deepest waters is less visible and therefore easier to ignore. It does not wash up on shore where people can see it. It lies in darkness, thousands of meters below the surface, out of sight, but not out of existence. The discoveries in places like the Mariana Trench serve as a powerful symbol. The Earth is a closed system. Materials we produce and discard do not vanish. They move, transform, and accumulate. Over time, they reach even the most distant corners of the planet. Scientists continue to investigate the full scale of deep-sea pollution. Each new expedition brings fresh evidence of how widespread the problem has become. Yet there is also hope. Understanding the extent of contamination is the first step toward change. Governments around the world have begun to ban certain single-use plastics. International agreements aim to reduce the release of harmful chemicals. Efforts to clean up coastal areas and improve waste management are expanding. Still, the challenge is enormous. Plastic production remains high. Many countries lack the infrastructure to manage waste effectively. Illegal dumping and accidental spills continue. Climate change adds another layer of complexity, as warming oceans and shifting currents may alter how pollutants move and settle. When future generations look back at this time, they may see it as a turning point. A moment when humanity realized that there are no remote corners beyond the reach of our influence. The deepest waters of the ocean, once thought to be eternal and untouched, now carry our signature. The question that remains is whether we will continue to add to that mark, or whether we will choose to lessen it. The deep ocean does not have a voice. It cannot protest or demand change. But through the work of scientists, it is telling a story of connection, consequence, and the surprising reach of human activity. From city streets to mountain rivers, from coastal shores to the blackest depths of the sea, everything is linked. And in the silent mud of the ocean floor, tiny fragments of plastic and traces of toxic chemicals testify to that connection in a way that no words ever could. The ocean is often described as a place of wonder, mystery, and beauty. From the surface, it can look calm and endless, stretching out like a sheet of moving glass beneath the sky. But when explorers leave the sunlight behind and descend into the deep sea, the world changes in ways that are hard to imagine. The colors disappear, the warmth fades, the sounds grow strange and distant, and inside the small metal shell of a submersible, human beings find themselves cut off from almost everything that makes them feel safe and grounded. In that isolated space, surrounded by crushing water pressure and endless darkness, the greatest danger is not always mechanical failure or sea creatures lurking outside. Sometimes the most powerful threat comes from within the human mind itself. Deep-sea exploration requires people to sit inside tiny submersibles for many hours at a time. These vehicles are built to survive extreme conditions. They are made of thick metal or special materials designed to withstand the enormous pressure of the ocean at great depths. The outside world, only a few meters away, could crush a human body in an instant. Yet inside the submersible, there is only a small compartment, often no bigger than a closet, where explorers must sit, sometimes barely able to stretch their legs. The air is recycled, the lighting is artificial. There are limited windows, sometimes just a small circular viewport. Every movement must be careful and controlled. There is no stepping outside for fresh air. There is no quick escape if panic begins to rise. One of the most common psychological dangers faced in these conditions is claustrophobia. Claustrophobia is the intense fear of being trapped in a small space. For someone who experiences this fear, even an elevator or a crowded room can cause sweating, racing heartbeat, and a sense of panic. Now imagine being sealed inside a metal sphere or cylinder thousands of meters below the surface of the ocean, knowing that you cannot open a door and walk out. Even explorers who do not normally suffer from claustrophobia may begin to feel discomfort after hours in such tight quarters. The walls seem closer. The air feels heavier. Every creak of the metal hull can sound like a warning. The mind has a powerful imagination. In darkness and silence, it often begins to create its own fears. When explorers descend into the deep sea, natural light disappears after a certain depth. Beyond roughly 1,000 meters, sunlight can no longer reach. The world outside becomes pitch black, except for the beams of artificial lights attached to the submersible. These lights reveal only a small circle of water ahead. Everything else remains hidden. This endless darkness can play tricks on the brain. Without visual reference points, it becomes difficult to judge distance or movement. The submersible may feel as if it is floating in empty space rather than water. Some explorers describe the sensation as being lost in the universe, drifting with no clear sense of direction. Sensory deprivation adds another layer of psychological strain. Sensory deprivation occurs when a person is cut off from normal sights, sounds, and physical sensations. In everyday life, people are surrounded by constant stimulation. There are voices, traffic noise, wind, sunlight, changing temperatures, and movement. All these signals help the brain stay active and balanced. Inside a deep-sea submersible, many of these inputs disappear. The temperature is controlled. The lighting does not change. The sounds are limited to the hum of equipment and the occasional ping of sonar. There is no fresh breeze, no smell of earth or trees, no variation in scenery beyond the small window view. When the brain does not receive enough stimulation, it can begin to react in unexpected ways. Some individuals may feel extreme boredom, which can slowly turn into restlessness and irritation. Others may experience anxiety as the lack of normal sensory input creates a feeling that something is missing or wrong. In rare cases, prolonged sensory deprivation can even cause mild hallucinations. The mind may imagine shapes in the darkness or misinterpret normal sounds as something threatening. A simple mechanical noise could suddenly seem like the sound of cracking metal or something tapping against the hull. Time perception also changes in isolation. Without sunlight or natural markers of time, it becomes difficult to judge how long one has been inside the submersible. Minutes can feel like hours. Hours can pass in what seems like a short while. This distortion of time can increase stress. If an explorer begins to feel anxious, every passing moment may feel stretched and heavy. Waiting for a long descent to finish, or for a slow ascent back to the surface, can test even the calmest mind. Another major psychological challenge is the awareness of danger. Deep-sea explorers are trained professionals. They understand the risks, they trust their equipment and their team, but no amount of training can completely erase the knowledge that they are in a hostile environment. At great depths, the water pressure is immense. It increases steadily with every meter of descent. Even though the submersible is built to handle this pressure, the mind can dwell on the what-if questions. What if there is a crack? What if a system fails? What if communication with the surface is lost? These thoughts can be especially powerful during long missions. Communication with the surface is often delayed or limited. Radio waves do not travel well through water, so deep-sea submersibles usually rely on acoustic communication, which can be slow and sometimes unclear. Explorers may feel cut off from the world above. If a technical issue occurs, they may have to solve it themselves, knowing that immediate rescue is unlikely. This isolation can increase feelings of vulnerability. Group dynamics inside the submersible can also affect mental health. Many submersibles carry only a small crew, sometimes 2 or 3 people. In such tight spaces, personal boundaries shrink. There is no private room, no place to step away if tension arises. Small disagreements can feel larger when there is no escape. If one person becomes anxious, that anxiety can spread to others. Emotional states are contagious, especially in confined environments. On the other hand, strong teamwork and trust can act as powerful protective factors. Explorers who know each other well and have trained together extensively often cope better with the psychological strain. They develop routines, share tasks, and communicate openly about their feelings. Humor can become an important tool. Sleep deprivation is another hidden psychological risk. Deep-sea missions can last many hours, sometimes more than half a day. The cramped conditions make it difficult to rest comfortably. The constant hum of machinery and the need to stay alert can prevent proper sleep. Lack of sleep affects mood, concentration, and decision-making. It can increase irritability and reduce the ability to manage stress. In a place where careful thinking is essential for safety, this can become dangerous. Physical discomfort adds to the mental strain. Sitting in the same position for long periods can cause muscle stiffness and pain. Limited bathroom facilities can create embarrassment or discomfort. Eating may be restricted to simple snacks or liquids. These small inconveniences may seem minor compared to the vast ocean outside, but over time they wear down a person's resilience. The darkness itself has a powerful psychological effect. Human beings evolved under the sun. For thousands of years, daylight guided daily life. Darkness often signaled danger. Even in modern times, many people feel uneasy in complete darkness. In the deep sea, darkness is not temporary. It is absolute and endless. The beams of the submersible's lights may reveal strange creatures or drifting particles, but beyond that small circle, there is only blackness. This can create a feeling of being watched, even when there is no visible threat. The imagination fills the unseen space. Some explorers report a strange sense of insignificance, as if they are tiny and fragile in a vast, uncaring world. This realization can be both awe-inspiring and unsettling. For some, it leads to a deep appreciation of nature's power. For others, it sparks anxiety about how small and vulnerable human beings truly are. Long-term psychological effects are also possible. While most deep-sea missions last hours rather than weeks, repeated exposure to extreme isolation can accumulate stress. Some explorers may experience lingering anxiety or vivid memories after returning to the surface. Loud noises might remind them of mechanical sounds in the submersible. Enclosed spaces may feel more uncomfortable than before. However, many also report positive psychological changes, such as increased confidence and a stronger sense of purpose. Training plays a crucial role in preparing explorers for these mental challenges. Before descending into the deep sea, crews undergo simulations and practice missions. They learn how to respond to emergencies calmly. They practice breathing techniques to manage anxiety. Some training programs include psychological screening to ensure that individuals are well suited for confined and high-pressure environments. Mental resilience is considered just as important as technical skill. Modern technology also helps reduce psychological strain. Improved lighting systems create a more natural interior environment. Better communication tools allow more regular contact with support teams on the surface. Cameras and monitors provide broader views of the surroundings, reducing the sense of blindness in the dark. Even small design improvements, such as slightly larger cabins or more comfortable seating, can make a significant difference. Despite these advances, the deep sea remains one of the most extreme environments humans choose to enter. The psychological dangers are real and powerful. Claustrophobia can grip the chest like an invisible hand. Sensory deprivation can blur the edges of reality. Isolation can amplify every fear and doubt. Yet at the same time, the deep sea offers something extraordinary. It offers discovery, knowledge, and the chance to witness life in forms few people will ever see. The human mind is both fragile and remarkably strong. In the confined darkness of a submersible, it can generate fear from silence, but it can also generate courage, curiosity, and wonder. Explorers who face the psychological dangers of deep-sea isolation often return with stories not only of strange creatures and alien landscapes, but also of their own inner journeys. They learn how they react under pressure. They discover strengths they did not know they had. When the submersible finally rises and breaks through the surface, sunlight floods the cabin once more. Fresh air fills waiting lungs. The wide horizon replaces the small circular window. The world feels larger and brighter than before. For a moment, the psychological weight lifts, but the memory of that silent, dark world below remains. There is a moment in every deep-sea mission when excitement quietly turns into something heavier. The crew has checked the weather. The engineers have inspected every bolt, wire, and seal. The submersible rests on the deck of a research vessel, small and fragile against the vast ocean stretching in all directions. Cameras flash. Scientists speak confidently about discovery, exploration, and the human desire to go where no one has gone before. Yet hidden beneath that confidence is a truth so serious that it is rarely spoken aloud. Once a submersible begins its descent into an ocean trench, it crosses a point from which rescue is almost impossible. This is the harsh reality of trench exploration. At shallow depths, divers can be reached. At moderate depths, submarines can be assisted. But at the crushing depths of the great ocean trenches, human beings enter a world where help cannot easily follow. The deeper a submersible sinks, the closer it moves toward what many engineers call the point of no return. It is not an official line drawn on a chart. It is not marked by a flashing light. It is a physical and technological limit shaped by pressure, darkness, distance, and time. Beyond that invisible line, survival depends entirely on the vessel's own systems. If those systems fail, rescue becomes nearly impossible. To understand why rescue is so difficult, we must first imagine the environment itself. Ocean trenches are the deepest parts of the sea. The most famous of them all is the Mariana Trench in the western Pacific Ocean. Within it lies a place known as the Challenger Deep, the deepest known point in the world's oceans. The depth there reaches nearly 11 kilometers, which is almost 7 miles beneath the surface. At that depth, the pressure is more than 1,000 times greater than the pressure we feel at sea level. Imagine stacking dozens of jumbo jets on top of a small car. That crushing force is pressing on every square inch of the submersible's hull. Pressure alone makes rescue extremely difficult. Most submarines operated by navies around the world cannot reach anywhere near such depths. Even advanced military submarines built with thick steel hulls and sophisticated technology are designed for much shallower operations. They are powerful and impressive machines, but they are not built to survive trench conditions. A rescue vessel must be able to withstand the same crushing pressure as the stranded submersible. Very few craft on Earth can do that. Only a handful of specialized deep-diving submersibles have ever reached the bottom of the deepest trenches. One of the earliest was the bathyscaphe Trieste, which descended into the Mariana Trench in the year 1960. That historic mission proved humans could survive the descent. Decades later, filmmaker and explorer James Cameron made a solo dive to Challenger Deep in the year 2012. Even more recently, the deep-sea vehicle DSV limiting factor has made repeated journeys to extreme depths. But these vehicles are rare, expensive, and few in number. They are not stationed around the world waiting for emergency calls. They are often located thousands of miles away from any potential accident. Now imagine a submersible descending into a trench when something goes wrong. Perhaps a battery system fails. Perhaps a leak forms in a seal. Perhaps the power system shuts down. If the vessel loses power, it may not be able to release its ballast weights, which are designed to make it float back to the surface. Without power, communication systems may also fail. The crew inside could be trapped in total darkness, unable to send a distress signal. At those depths, even a small mechanical problem can quickly turn into a life-threatening emergency. Communication underwater is already limited at shallow levels. Radio waves do not travel well through seawater. Submersibles rely on acoustic communication, sending sound signals to the surface. But sound signals weaken over long distances. In the deepest trenches, communication can be slow, distorted, or completely lost. If a submersible stops responding, the support ship above may not even know its exact position. It may only have an approximate location based on its last signal. Searching for a missing submersible at trench depths is like searching for a tiny object in a vast, pitch-black desert. The ocean floor in trench regions is not smooth. It is uneven, filled with slopes, cliffs, and loose sediment. Strong underwater currents can shift a disabled vehicle. If the craft has imploded due to pressure, debris could be scattered over a wide area. If it has landed intact but powerless, it may be partially buried in soft sediment. Every hour that passes makes the search more difficult. Time is the most unforgiving enemy in such situations. Submersibles carry a limited supply of oxygen. Even in well-designed vehicles, life support systems are built with careful calculations. Engineers estimate how much oxygen the crew will consume and how much carbon dioxide must be removed from the air. Emergency reserves are included, but they are not endless. If a submersible becomes trapped at the bottom of a trench, the crew's survival time may be measured in hours or, at best, a few days. Organizing a rescue mission, locating the craft, and sending down a vehicle capable of reaching that depth would likely take far longer. Launching a rescue operation in deep ocean conditions is a massive task. First, a ship capable of handling deep-sea equipment must travel to the location. That alone can take days, depending on distance and weather. Once on site, specialized remotely operated vehicles or deep-diving submersibles must be deployed. Each descent to extreme depth can take several hours. Reaching the bottom of the Mariana Trench, for example, takes around 4 hours of descent and another 4 hours to return to the surface. That means a single rescue attempt could consume an entire day, even under perfect conditions. Weather adds another layer of difficulty. Ocean trenches are often located in remote regions of the Pacific. Storms can delay rescue ships. Rough seas can make it dangerous to launch and recover submersibles. High waves and strong winds increase the risk to both rescuers and equipment. A rescue operation cannot simply begin at once. It must wait for safe conditions. Even if a rescue vehicle reaches the stranded submersible, the challenges continue. How will it attach lifting cables? Does the disabled craft have external handles designed for towing? Is it stuck in sediment? If the hull is damaged, attaching cables could cause further harm. If the vessel has imploded, rescue is no longer possible. The crushing pressure at such depths can cause an implosion in a fraction of a second, leaving no survivors. The tragic loss of the submersible Titan in the year 2023 reminded the world how unforgiving the deep ocean can be. Although that incident occurred at depths far shallower than the deepest trenches, it showed how limited rescue options truly are. Even with international attention, advanced technology, and multiple ships searching, the outcome was tragic. That event happened at a depth of around 4,000 meters. Now imagine trying to mount a rescue at nearly 11,000 meters. Another problem is that trench missions are rare. Unlike naval submarines which operate regularly and have established rescue systems, deep trench expeditions are usually scientific or exploratory missions. They are conducted by small teams, sometimes private organizations, sometimes research institutions. There is no global emergency network dedicated solely to trench rescue. There are submarine rescue systems for military vessels, but those are designed for depths of several hundred meters, not thousands. Let us consider the physics more closely. At extreme depth, the pressure increases by about 1 atmosphere for every 10 meters of water. By the time a submersible reaches 11,000 meters, it is experiencing more than 1,000 atmospheres of pressure. That force pushes inward on every surface. If the hull has even a tiny flaw, microscopic cracks can grow. Materials behave differently under such stress. Metals can become brittle, seals can deform, electronics can fail under intense pressure and cold. Temperature is another factor. In the deepest trenches, the water temperature is only a few degrees above freezing. Cold affects batteries, hydraulics, and electronic systems. If a vehicle loses power, it cannot generate heat. The interior temperature may begin to drop. The crew could face hypothermia even if the hull remains intact. There is also the problem of buoyancy. Submersibles descend by carrying heavy ballast weights. To rise, they release those weights. This system is usually designed to work even if power fails, using mechanical releases that depend on gravity. But if the mechanism jams, or if the vehicle is damaged, it may not be able to shed weight. Without releasing ballast, it cannot float upward. Some might ask why rescue submersibles cannot simply be kept on standby. The answer lies in cost and practicality. Building a deep trench-capable vehicle is extremely expensive. Maintaining it requires specialized crews and equipment. There are only a few such vehicles in existence. They are often booked for research missions around the world. Keeping one permanently stationed near every trench would be impossible. Distance is another silent obstacle. The Mariana Trench lies thousands of kilometers from major ports. Even reaching the area requires long sea voyages. Air transport is limited because the equipment is massive and delicate. By the time a rescue vessel could arrive, precious time would have been lost. Furthermore, operating at extreme depth pushes technology to its limits. Cables must be long and strong enough to handle enormous tension. Winches must lift heavy loads from miles below. Fiber optic lines used for communication can snap under strain. Every piece of equipment must survive pressure, cold, and darkness. The psychological reality of trench exploration is equally important. Every crew member knows that once they begin their descent, they are entering a zone where outside help cannot quickly reach them. This knowledge creates a unique kind of mental pressure. Unlike astronauts in low Earth orbit, who can potentially return within hours, trench explorers cannot simply fire engines and rise quickly. Their ascent takes hours. They are isolated from the world in a small sphere of metal and composite material. Many explorers describe a strange calm during descent. The sunlight fades. The ocean turns from blue to black. Bioluminescent creatures flicker in the darkness like distant stars. The submersible creaks under pressure, making small popping sounds as the hull adjusts. Each sound is harmless, yet it reminds the crew of the immense force outside. They trust the engineering. They trust the calculations. but they also understand that trust is all they have. The idea of a point of no return becomes more real the deeper they go. At certain depths, rescue submarines used by navies can no longer operate. Beyond that, only specialized research vehicles can reach them. And beyond an even deeper threshold, perhaps only 1 or 2 vehicles in the world have the capability. If those vehicles are unavailable or too far away, rescue becomes a theoretical possibility rather than a practical one. Search operations at extreme depth rely heavily on remotely operated vehicles, or ROVs. These machines are connected to surface ships by long cables. They carry cameras, lights, and robotic arms. But even ROVs have limits. Their cables can become tangled. Their movement is slow. In strong currents, control becomes difficult. And if the trench walls are steep, navigation can be dangerous. Another factor is sediment. The floor of many trenches is covered with fine, soft mud. If a submersible lands hard or sinks slightly into sediment, it can become stuck. Trying to pull it free may require enormous force. If the vehicle is fragile due to damage, pulling too hard could cause further failure. There is also the issue of mapping. Although modern sonar systems have mapped large portions of the ocean floor, detailed maps of trench interiors are still incomplete. Some areas remain unexplored. A stranded submersible could rest in a crevice or behind a ridge, hidden from sonar scans. Energy supply presents another limit. Surface ships must maintain position directly above the rescue site. This requires powerful engines and fuel. In rough seas, holding position becomes more challenging. Dynamic positioning systems can fail. Without accurate positioning, cables and vehicles may drift off target. Every part of a rescue operation would need to work perfectly. The search must locate the submersible quickly. Weather must remain stable. Equipment must function without failure. The stranded vessel must remain intact long enough for help to arrive. All these conditions must align. The odds are not favorable. Because of these realities, trench missions are designed with extreme caution. Engineers assume that rescue may not be possible. They focus on preventing failure rather than planning recovery. Redundant systems are installed. Backup communication lines are included. Life support reserves are calculated carefully. Materials are tested under pressures even greater than expected. Every bolt and seal is examined. Yet no engineering system is perfect. The ocean is a harsh teacher. It does not forgive mistakes. The crushing pressure does not care about human ambition. It does not negotiate. When people speak of exploration, they often think of space. Yet in many ways, trench exploration is even more unforgiving. Astronauts aboard the NASA missions orbiting Earth can be reached within days. The distance to low Earth orbit is a few hundred kilometers. The distance to the bottom of the Mariana Trench is only 11 kilometers. But the barrier is pressure, not distance. That barrier is harder to overcome. If a spacecraft loses power in orbit, it may still communicate. Rescue missions can be planned. But if a submersible loses power at trench depth and cannot release ballast, it may simply remain on the seabed. There is no easy way to tow it upward without specialized equipment. In truth, the phrase rescue impossibility does not mean rescue is absolutely impossible. It means that rescue is so difficult, so slow, and so uncertain that survival cannot depend on it. Every descent into a trench must be treated as self-contained. The crew must assume that they alone are responsible for their safe return. This knowledge shapes the culture of deep-sea exploration. It creates respect for preparation. It encourages careful testing and gradual progress. It also adds a sense of bravery to every mission. When explorers descend into a trench, they are not only seeking knowledge, they are accepting risk at a level few others would. The ocean trenches remain among the least explored places on Earth. They hold mysteries about geology, biology, and the history of our planet. They may contain new species, new chemical processes, and clues about life's origins. The desire to explore them is powerful, but so is the reality that beyond a certain depth, help cannot easily reach you. That is the point of no return. It is not a dramatic line drawn in red. It is a quiet understanding shared by engineers and explorers alike. It is the moment when descent becomes commitment. It is the depth at which rescue changes from difficult to nearly impossible. And so, every time a submersible slips beneath the waves and begins its long fall into darkness, it carries with it more than cameras and sensors. It carries human courage, it carries trust in science and engineering, and it carries the unspoken awareness that in the deepest parts of the ocean, survival depends not on rescue, but on the strength of the vessel and the precision of its design. In those silent depths, where pressure crushes steel and darkness swallows light, there are no second chances. There is only preparation, resilience, and hope that the journey down will always be matched by a safe return to the world above. Barotrauma is a word that describes physical damage caused by changes in pressure. The term comes from words meaning pressure and injury. It happens when there is a difference between the pressure outside the body and the pressure inside air-filled spaces within the body. Humans have many such spaces. The lungs are the most obvious, but there are also the sinuses, the middle ear, and even tiny pockets of gas in the digestive system. When the outside pressure rises or falls faster than the body can adjust, tissues can tear, burst, or collapse. Imagine a diver slowly descending beneath the surface. As they go down, the water presses harder and harder. The air inside their lungs and other air spaces becomes compressed. If the diver is breathing properly from a tank that supplies air at the same pressure as the surrounding water, the body can remain in balance. But if something goes wrong, the danger is immediate. If a diver were to hold their breath while rising to the surface, for example, the air in their lungs would expand as the pressure decreases. That expanding air needs space. If it cannot escape, it can tear the delicate tissues of the lungs. This is a form of barotrauma known as pulmonary barotrauma. It can cause air to leak into places where it does not belong, such as the bloodstream or the chest cavity. In extreme cases, it can lead to sudden death. Now take this idea and imagine it not at shallow diving depths, but at the deepest parts of the ocean. Ocean trenches plunge thousands of meters down. At those depths, the pressure is not just uncomfortable, it is overwhelming. It can be hundreds of times greater than what we feel at the surface. If a human body were suddenly exposed to that kind of pressure without protection, the result would not be slow discomfort. It would be instant and devastating compression. Air-filled spaces would collapse almost immediately. The lungs would shrink violently. The eardrums would likely rupture. Blood vessels could tear. It would be impossible to survive. The opposite situation is just as deadly. Suppose somehow a person were brought from trench depth to the surface in an instant. The pressure outside the body would drop dramatically. Any gases dissolved in the blood under high pressure would suddenly form bubbles. This is decompression sickness, sometimes called the bends. Under high pressure, gases like nitrogen dissolve into the blood and tissues. This is similar to how a sealed bottle of soda holds carbon dioxide dissolved in liquid. When you open the bottle, the pressure drops and bubbles form. Inside the human body, those bubbles can block blood vessels, damage nerves, and cause intense pain. In severe cases, they can lead to paralysis, stroke-like symptoms, or death. Decompression sickness has been known for many years, especially among divers and workers who once built tunnels underwater or under rivers. In the past, people working in pressurized chambers often became sick when they returned too quickly to normal air pressure. They would feel sharp pain in their joints, dizziness, or even collapse. Over time, scientists learned that slow, controlled ascent was necessary to allow gases to leave the body safely. Divers today follow strict schedules, rising in stages and sometimes pausing for long periods to avoid dangerous bubble formation. But these safety methods only apply to certain depths. The deeper a diver goes, the more complicated and risky the return becomes. At trench depths, the pressure is so extreme that no human diver can go there in a simple diving suit. Special submersibles are used instead. These vehicles are built with thick walls designed to withstand crushing forces. Inside, the pressure is kept close to normal surface levels so that the people within can survive. If that protective shell were to fail, the result would be catastrophic. The water would rush in with enormous force. The sudden pressure change would destroy the air-filled space in an instant. It would not be a slow drowning. It would be an implosion, faster than a blink. Barotrauma does not only affect the lungs and ears. The sinuses, small air pockets in the skull, can become painfully squeezed during descent if pressure is not equalized. Divers often feel this as pressure in the face. If equalization fails, tissues can swell and bleed. The middle ear is particularly vulnerable. The eardrum is thin and sensitive. If the pressure outside becomes much greater than the pressure inside, the eardrum can rupture. This is extremely painful and can cause hearing loss and dizziness. In trench conditions, these injuries would not simply be painful, they would be immediate and overwhelming. The body is built for life on land, where pressure changes are small and gradual. Even flying in an airplane, which involves a drop in air pressure, requires careful control in the cabin to prevent discomfort. The difference between surface pressure and trench pressure is far greater than anything we encounter in daily life. It is a difference so vast that survival without advanced engineering is impossible. There is also the issue of gas toxicity at high pressures. As pressure increases, gases behave differently. Nitrogen, which makes up most of the air we breathe, can have strange effects under pressure. Divers at great depths sometimes experience nitrogen narcosis, a condition that can cause confusion, poor judgment, and a feeling similar to being intoxicated. The deeper they go, the stronger these effects become. At even greater pressures, oxygen itself can become toxic, leading to seizures or other life-threatening problems. This means that even if the body could physically withstand the pressure, the very act of breathing becomes dangerous. To reduce these risks, deep divers sometimes use special gas mixtures instead of normal air. Helium is often added because it has different properties under pressure, but even with carefully designed mixtures, there are limits. Human physiology can only adapt so far. Beyond certain depths, no combination of breathing gases can make it safe. The pressure becomes too great, the body too stressed, and the risks too high. Another hidden danger lies in the structure of our blood vessels and tissues. The human body contains many fluids and soft tissues that can be compressed. While fluids do not compress as easily as gases, the overall structure of organs can still be distorted under extreme force. Tiny capillaries, which carry blood to every cell, can rupture. The heart, which depends on delicate pressure differences to pump blood, may not function properly if the external pressure overwhelms the body's natural systems. Consider also the psychological shock of rapid decompression. If a pressurized environment suddenly fails, the drop in pressure can cause not only physical harm, but also extreme disorientation. Vision can blur, hearing can fail, consciousness can be lost within seconds. The brain depends on steady oxygen supply and stable conditions. Rapid pressure shifts interfere with both. Even if someone were rescued quickly, the damage could already be irreversible. There is something almost cruel about how unforgiving pressure is. Other dangers in the ocean, such as cold or darkness, can sometimes be managed with proper clothing and equipment. Pressure, however, is constant and relentless. It presses equally in all directions. It finds every weakness. A tiny crack in a submersible hull can lead to disaster. A small mistake in ascent speed can cause decompression sickness. A brief moment of panic and a held breath during ascent can lead to lung rupture. When explorers descend into the deepest parts of the ocean in specially built craft, they trust not only the strength of the vessel, but also careful planning. Every detail is calculated. The materials are tested again and again. The descent is slow and controlled. The ascent is just as careful. Even then, the risks cannot be reduced to zero. The ocean floor at trench depth is one of the most hostile environments on Earth, not because it burns or freezes, but because it squeezes. The impossibility of surviving decompression from trench depths becomes clear when we think about the scale of change involved. The difference in pressure between the bottom of a deep trench and the surface is enormous. If someone were exposed directly to that difference without gradual adjustment over an extended period, the gases in their body would violently expand. Blood vessels would become blocked by bubbles. Organs would suffer damage. The lungs could tear. The nervous system could be disrupted in ways that stop breathing and heart function almost immediately. In fiction, characters sometimes travel from crushing depths to the surface in moments, shaking off the experience as if it were nothing. In reality, even trained divers working at much shallower depths must spend long periods decompressing. They may stop at various levels, waiting patiently while their bodies release dissolved gases safely. If they rush, they risk severe pain and lasting injury. From trench depths, safe decompression would not simply take hours. It could take an impractical and possibly unmanageable length of time, assuming survival at depth were possible in the first place. There is also the problem of pressure's effect on equipment. Diving suits designed for shallower depths would be crushed long before reaching trench levels. Even rigid suits have limits. Submersibles must be carefully engineered with thick walls and strong shapes, often spherical, because spheres distribute pressure evenly. A flat surface would buckle more easily. The engineering challenge alone shows how extreme the environment is. If steel and advanced materials struggle against these forces, what chance would unprotected human tissue have? When we study barotrauma and decompression risks, we are reminded of a simple truth. The human body is a product of its environment. We evolved in air, under one atmosphere of pressure. Our lungs inflate and deflate easily at that level. Our ears balance small changes. Our blood chemistry works within narrow limits. Push those limits too far, too fast, and the system breaks down. This does not mean exploration must stop. It means it must be done with respect for the laws of physics and the limits of biology. Engineers design vehicles that keep the inside at near normal pressure. Scientists plan dives carefully. Divers train extensively to understand how to equalize pressure, control breathing, and follow decompression schedules. Every rule exists because someone, at some point, suffered the consequences of ignoring it. Barotrauma and decompression risks are not dramatic in the way a storm or a shark attack might be. They are silent threats. You cannot see pressure, you cannot hear it. Yet it is always there, waiting to assert itself if conditions change. If a human were suddenly exposed to trench pressure, survival would be impossible. If a human were suddenly brought from trench pressure to the surface without protection and controlled decompression, survival would also be impossible. Between those two extremes lies a narrow path of safety, carved out by science, engineering, and careful procedure. That narrow path allows us to visit places we were never meant to inhabit, but only briefly, and only inside protective shells. In the end, the story of barotrauma and decompression is a story about limits. It is about the boundary between our fragile biology and the immense forces of the natural world. The ocean's deepest trenches are not evil or hostile in intention. They simply exist under conditions that are utterly different from those at the surface. When we cross into that realm, we must carry our own safe environment with us. Without it, the change in pressure alone would be swift, merciless, and final. Understanding these risks does more than protect divers and explorers. It deepens our respect for the ocean and for the delicate balance that keeps us alive on land. It shows how finely tuned our bodies are to a specific set of conditions and how quickly that balance can be lost. And it reminds us that even in an age of advanced technology, there are still places on Earth where survival depends entirely on careful planning, precise engineering, and a profound respect for the unseen force of pressure. One of the earliest and most dramatic deep-sea missions took place in the year 1960. Two men, the Swiss engineer and oceanographer Jacques Piccard and United States Navy Lieutenant Don Walsh, climbed into a small submersible called Trieste. Their goal was bold and almost unbelievable at the time: to reach the deepest known point in the ocean, the Challenger Deep in the Mariana Trench. No human had ever gone that far down. The vessel they used was unlike a traditional submarine. It was more like a floating balloon attached to a steel sphere. The steel sphere, just large enough for two men to sit inside, was their only protection against the immense pressure of the deep. As the Trieste began its descent, it moved slowly into darkness. The sunlight faded quickly. The water grew colder. Outside the sphere, the pressure increased with every passing meter. By the time they approached the bottom, the pressure outside was so intense that it was equal to thousands of tons pressing against the small metal cabin. During the descent, something terrifying happened. A loud cracking noise echoed through the cabin. One of the outer windows, made of thick plexiglass, had cracked under pressure. In that moment, Piccard and Walsh had to decide whether to continue or abort the mission. Imagine sitting in a metal ball surrounded by miles of water, hearing the sound of material giving way. They did not know if the crack would spread. They did not know if the sphere would fail. Yet after checking their instruments and discussing calmly, they continued downward. It was a decision that could have cost them their lives. When they finally reached the bottom after nearly 5 hours of descent, they found themselves resting on the ocean floor more than 10,000 meters below the surface. The landing stirred up fine sediment, creating a cloudy view outside. They stayed for only about 20 minutes before beginning the long journey back up. Their ascent took several more hours. When they finally broke the surface, they had made history. But it was a close call. If that cracked window had failed, the immense pressure would have crushed the sphere instantly. Their success came hand in hand with extreme risk. Decades later, another explorer would attempt a solo journey to the same abyss. In the year 2012, film director and deep-sea explorer James Cameron descended alone in a specially designed submersible called Deep Sea Challenger. Cameron was already known around the world for directing epic films, but his passion for the ocean was just as strong. He wanted to return to the Challenger Deep and conduct scientific research while proving that a single pilot could survive the journey. Unlike the Trieste, the Deep Sea Challenger was a narrow, vertical craft. Cameron lay almost upright inside a small sphere barely large enough to move. The descent was faster than the Trieste's, but the dangers were no less real. As he dropped deeper and deeper, systems had to function perfectly. Oxygen levels, carbon dioxide removal, battery power, communications, ballast release systems, any one of these failing could have turned the mission into a tragedy. During the dive, some of Cameron's equipment began to malfunction. Thrusters did not respond as expected. Communication with the surface support ship became unreliable. At one point, hydraulic fluid leaks were reported. Though none of these failures were immediately fatal, they added layers of danger. Cameron later described the experience as both beautiful and extremely tense. Alone in the deepest place on Earth, surrounded by total darkness and enormous pressure, he had no backup pilot sitting beside him. If something catastrophic happened, rescue would have been impossible. He spent only a short time at the bottom before deciding to ascend earlier than planned due to equipment issues. His safe return was celebrated around the world. Yet behind the headlines was a simple truth. Even with modern technology, the deep ocean remains unpredictable and unforgiving. The dangers are not limited to the Mariana Trench. In the year 1934, long before anyone reached the deepest trench, two American explorers, William Beebe and Otis Barton, descended into the ocean inside a steel sphere known as the bathysphere. They were lowered by cable off the coast of Bermuda. The bathysphere was attached to the surface ship by a single steel cable. If that cable snapped, there was no backup. They would have sunk helplessly to the bottom. The bathysphere had no independent power, No engine, no ability to move freely. It was simply lowered and raised like a heavy weight. During their descents, Beebe and Barton experienced moments of extreme anxiety. Cables creaked, the sphere groaned under pressure. They described hearing strange sounds outside, which may have been sea creatures or simply the metal adjusting to pressure. Each dive required absolute trust in the cable and the crew above. A single mistake could have sent them plunging into darkness forever. Their courage opened the door to modern deep-sea exploration, but their equipment was basic and risky. In one dive, communication lines malfunctioned, cutting off their connection to the surface. For a brief and frightening time, they were alone in the dark, unsure whether the crew could hear them or even knew their condition. Eventually, communication was restored, but those minutes must have felt endless. Not all deep-sea missions ended safely. The ocean has claimed lives. Though most trench explorations have been carefully planned, accidents in deep-sea submersibles have occurred over the years. Equipment failure under extreme pressure is always a possibility. Seals can fail. Electrical systems can short-circuit. Ballast systems, which allow a submersible to rise back to the surface, can malfunction. If ballast weights do not release, a craft may remain trapped below. In some research dives across various deep ocean trenches, submersibles became tangled in undersea cables or fishing nets. Others experienced battery failures that forced emergency ascents. In a few cases, small fires broke out inside submersibles due to electrical faults. In the tight, oxygen-controlled space of a deep-sea craft, even a small fire can be deadly. Crews train for such events, but training cannot remove the fear when alarms sound in a confined metal sphere miles below the surface. One of the most chilling aspects of trench exploration is the knowledge that rescue is almost impossible at extreme depths. On land, if a climber becomes trapped on a mountain, rescue teams may attempt to reach them. In shallow waters, divers can sometimes assist a damaged submarine, but at depths beyond several thousand meters, there is no practical rescue option. The pressure is too great. The time needed to organize help would be too long. Explorers know this before they descend. They accept that their survival depends entirely on their equipment and their preparation. There have also been near disasters involving remotely operated vehicles, known as ROVs. These robotic explorers are often sent ahead of human missions. In some cases, ROVs have been crushed by pressure after structural weaknesses were exposed. Others became stuck in hydrothermal vent fields where superheated water and toxic chemicals damaged sensitive parts. Though robots do not risk human lives directly, their failures highlight how harsh the environment truly is. If a robot built from advanced materials can be destroyed, what about a vessel carrying people? Earthquakes add another layer of danger. Many of the world's deepest trenches lie along tectonic plate boundaries. The Mariana Trench, for example, sits within the seismically active Pacific region, often referred to as the Ring of Fire. Sudden seismic activity can trigger underwater landslides or create powerful currents. A submersible resting on the trench floor during such an event could be buried or tossed violently. Some expeditions have reported unexpected strong currents even at extreme depths. These currents can push a submersible off course or into rocky walls. Navigation is difficult when there is no natural light and limited sonar visibility. Pilots rely on instruments, but instruments can fail. When that happens, confusion sets in quickly. Psychological pressure is another invisible danger. Sitting in a tiny space for hours, sometimes alone, surrounded by darkness, and knowing that the weight of the ocean could crush you instantly, can affect even the calmest mind. Explorers have spoken of moments when fear creeps in quietly. The hum of machinery becomes louder. Every small sound seems threatening. Training and focus are essential to prevent panic. There have been missions where carbon dioxide levels inside a submersible began to rise unexpectedly due to scrubber system problems. High carbon dioxide can cause dizziness, confusion, and eventually unconsciousness. Crews must monitor air quality constantly. A simple mechanical failure in the life support system could turn a scientific mission into a fight for survival. Despite all these dangers, people continue to explore. Why? Because the deep ocean holds secrets about life, geology, and the history of our planet. Every successful dive expands human knowledge, yet every dive also carries risk. The history of trench exploration is not just a story of triumph. It is a story of close calls, cracked windows, failing cables, malfunctioning thrusters, and tense decisions made in darkness. When we look back at the courage of Jacques Piccard and Don Walsh in 1960, or James Cameron in 2012, we see more than achievement. We see individuals who faced the unknown and accepted the possibility of death in the pursuit of discovery. Their experiences remind us that the ocean is not conquered. It is visited briefly, with humility and respect. The trenches remain among the most dangerous environments on Earth. Technology continues to improve, materials grow stronger, systems become more reliable, but the fundamental truth remains unchanged. The deeper we go, the less room there is for error. One small crack, one failed seal, one electrical spark, that is all it takes. Historical disasters and near-death experiences in ocean trenches teach us important lessons. They show the limits of human engineering. They highlight the bravery of explorers. They remind us that even in the modern age, parts of our own planet are as hostile and mysterious as distant worlds. And as long as curiosity drives us downward into the dark, the line between discovery and disaster will remain thin, fragile, and unforgettable. Navigation inside an ocean trench is one of the hardest tasks human beings have ever attempted. It is not simply a matter of driving a machine underwater and looking around. It is more like trying to move through an endless night where there is no sky, no stars, no landmarks, no horizon, and no sense of direction. Everything is dark, everything is cold, everything is under crushing pressure. And yet, explorers continue to descend into these deep scars in the ocean floor, determined to map them, study them, and understand what secrets they hold. The deeper they go, the more they realize that the greatest danger is not always a monster from the dark or a sudden earthquake. Sometimes the most serious threat is simply getting lost. An ocean trench is not a flat space. It is not smooth or easy to travel across. It is shaped like a massive wound in the Earth's crust, a deep valley that stretches for hundreds of miles. Its walls can be steep and uneven. Its floor can be covered in thick layers of soft sediment that swallow equipment like quicksand. There are ridges, cracks, hidden slopes, and sudden drop-offs. In many places, the trench twists and bends, forming narrow passages and sharp turns. Trying to map such a place is like trying to draw a picture of a mountain range while blindfolded. Light does not reach these depths. Sunlight fades away long before a submersible reaches the deepest parts of a trench. After descending beyond about 1,000 meters, natural light disappears completely. From that point on, everything depends on artificial lights mounted on the submersible. But even these lights do not travel very far. The beams cut through the dark for a short distance, then fade into blackness. The water absorbs the light, and tiny particles floating in the water scatter it. Instead of a clear view, explorers often see a snowstorm of drifting specks illuminated in the beams of their own lamps. Beyond that short, glowing circle, there is nothing but endless night. Without light, humans lose their strongest sense. On land, we depend on our eyes to understand where we are. We look at the sky to know up from down. We look at the ground to judge distance. We see buildings, trees, and mountains to orient ourselves. In the trench, none of this exists. There is no sky above and no clear ground below, only darkness in every direction. A pilot inside a submersible must rely on instruments instead of instinct. They cannot trust their own senses, because in the deep ocean, those senses can be deceived. Mapping a trench requires careful measurement of its shape. Scientists use Sonar, which stands for Sound Navigation and Ranging. Instead of light, sonar uses sound waves. A device sends out a pulse of sound. That sound travels through the water until it hits something solid, like the seafloor or a rock wall. The sound then bounces back to the sender. By measuring how long it takes for the echo to return, computers can estimate the distance to the object. In this way, sonar can create a picture of the underwater landscape. However, sonar has limits. In shallow water, it can produce detailed maps. In deep trenches, the situation becomes more complicated. The water pressure at extreme depths changes how sound travels. Temperature differences in layers of water can bend sound waves. Salinity, which is the amount of salt in the water, also affects how sound moves. These factors can cause sonar signals to scatter or weaken. Instead of a sharp image, the result may be blurry or incomplete. It is like trying to see through thick fog. In addition, trenches are often very narrow compared to their depth. When a sonar pulse is sent out in such a confined space, the sound can bounce off multiple surfaces. It may hit one wall, then the other, then the floor, creating overlapping echoes. The returning signals can confuse the system. The computer must sort out which echo came from which surface. Mistakes can happen. A false reading could make a cliff look like a slope, or a flat surface look like a hole. In a place where a single error can lead to disaster, this uncertainty is dangerous. Another challenge comes from the limited range of sonar. The deeper the trench, the farther the sound must travel before returning. Over long distances, sound waves lose strength. They spread out and fade. The deeper the submersible, the weaker the echo may become. To compensate, stronger pulses can be used, but this requires more energy and can disturb marine life. There is always a balance between gathering clear information and protecting the environment. Communication adds another layer of difficulty. Radio waves, which are used for communication on land and in the air, do not travel well through seawater. The salt in the water blocks them. That means a submersible cannot simply use regular radio to speak to a ship on the surface. Instead, it must rely on acoustic communication, which uses sound waves. But sound travels much slower than radio waves. When a submersible sends a message to the surface, there is a delay before it is received. If the trench is very deep, that delay can be several seconds. In an emergency, those seconds can feel like an eternity. Imagine a pilot facing a sudden problem, such as a mechanical failure or an unexpected obstacle. They send a message to the support ship asking for guidance. They must then wait in silence for a reply. In that waiting period, the situation may worsen. The pilot must often make decisions alone, using their training and judgment. The delay in communication means that help is never instant. In the deep ocean, you are always somewhat alone. Maintaining orientation is another serious challenge. On land, gravity tells us which way is down. Our inner ears help us maintain balance. In a submersible, however, the environment can be confusing. The vehicle may tilt while descending along a slope. It may rotate slightly while adjusting position. Without clear visual references, the pilot might not immediately realize the exact angle of the vehicle. Instruments provide data about pitch, roll, and depth, but the human brain sometimes struggles to match that information with what little it can see outside. Sediment clouds make the situation even worse. The floor of a trench is often covered in very fine mud. When a submersible moves too close to the bottom, its thrusters can stir up this sediment. A thick cloud of particles can rise and surround the vehicle, reducing visibility to almost zero. In such conditions, even the limited light from the submersible's lamps becomes useless. The pilot must rely entirely on sonar and instruments. It becomes a slow, careful process of feeling the way forward through sound. The walls of trenches can also be unstable. Small landslides can occur without warning. Rocks and sediment may shift and fall. If a submersible is navigating close to a steep wall, a sudden collapse could block its path or damage its hull. Accurate maps are essential to avoid such hazards, but as mentioned earlier, Creating precise maps is extremely difficult. There is always a risk that the actual terrain differs slightly from what the instruments suggest. Currents in the trench can further complicate navigation. Although deep waters are often calmer than surface waters, slow but steady currents can still exist. These currents may not be obvious at first. A submersible trying to hover in place may slowly drift without the pilot realizing it. Over time, this drift can carry the vehicle off its planned path. In a narrow trench, even a small sideways movement could bring the submersible dangerously close to a wall. Navigation systems, such as global positioning systems, commonly used on land and at sea, do not work underwater at great depths. Signals from satellites cannot reach the trench floor. Instead, explorers use specialized underwater positioning systems. These often involve placing acoustic transponders on the seafloor. The submersible communicates with these devices to determine its location, but setting up such a system requires time, planning, and prior knowledge of the area. In unexplored trenches, there may be no existing network to rely on. The deeper the trench, the greater the pressure. At extreme depths, the pressure can be more than 1,000 times the pressure at sea level. This immense force presses against every part of the submersible. While modern engineering allows vehicles to withstand these forces, the pressure still affects instruments. Sensors must be carefully designed and tested. Even a small failure in a navigation instrument could lead to incorrect readings. Battery life also limits exploration. Submersibles and autonomous underwater vehicles rely on stored energy. Powerful lights, sonar systems, communication equipment and thrusters all consume electricity. The more tools that are used to navigate safely, the faster the energy supply is drained. Pilots must constantly monitor their remaining power. They must plan their route carefully to ensure they can return to the surface before the batteries run out. Running out of power in a trench would be catastrophic. Autonomous underwater vehicles which operate without a human pilot on board face their own navigation challenges. These robotic explorers are programmed with instructions before they descend. They rely on preloaded maps and sensor data to adjust their path. However, if they encounter unexpected terrain or obstacles, they must decide how to respond on their own. Advanced algorithms help them avoid collisions, but no system is perfect. Recovering a lost robot from the depths can be extremely difficult and expensive. Time perception changes in the trench. In complete darkness, without sunrise or sunset, it becomes hard to feel the passage of hours. Inside a submersible, the crew may focus intensely on instruments and procedures. The outside world fades away. Without natural cues, fatigue can set in quietly. Tiredness affects judgment. In a place where every decision matters, mental sharpness is essential. Despite all these challenges, mapping and navigating trenches is incredibly important. Trenches hold clues about Earth's history. They are places where tectonic plates meet and move. They may contain unique life forms adapted to extreme conditions. They may even hide valuable minerals. To study these features safely, explorers must first understand the terrain. That requires patience, precision, and constant improvement of technology. Over the years, advances in sonar imaging have improved our ability to map deep areas. Multi-beam sonar systems send out many sound pulses at once, covering a wider area. High-resolution sensors can detect smaller details. Improvements in computer processing allow faster analysis of returning echoes. Still, even with modern technology, large portions of the world's trenches remain only roughly mapped. In some cases, scientists have better maps of the surface of Mars than of certain parts of our own ocean floor. The psychological impact of navigating in complete darkness should not be underestimated. Humans evolved under open skies, guided by sunlight and stars. Being in a small metal sphere surrounded by crushing pressure and endless blackness can be unsettling. Every sound inside the vehicle, every creak of metal adjusting to pressure can feel amplified. Trust in equipment and training becomes essential. the pilot must remain calm, steady, and focused. When mapping missions succeed, they reveal stunning landscapes. There are towering cliffs, winding canyons, and strange formations shaped by geological forces over millions of years. Each successful navigation mission adds a piece to the puzzle. Gradually, the blank spaces on our maps shrink. But the process is slow and demanding. Communication delays also affect coordination between multiple vehicles. Sometimes, a mission may involve both a piloted submersible and one or more robotic units. Coordinating their movements in a trench requires careful timing. Because sound-based communication has delays, commands cannot be adjusted instantly. Each vehicle must operate with a degree of independence. Clear planning before descent is essential. Emergencies highlight the importance of navigation skills. If a submersible becomes tangled in debris or stuck in soft sediment, knowing its exact position is critical for rescue planning. Surface teams need accurate coordinates to attempt recovery. If location data is uncertain, search efforts become much harder. In the vast darkness of a trench, even a small area can feel impossibly large. Scientists continue to develop new tools to overcome these challenges. Inertial navigation systems measure movement using accelerometers and gyroscopes. By tracking every small motion, these systems estimate position over time. However, small errors can build up. Without external reference points, the calculated position may slowly drift from the true location. Combining inertial systems with acoustic positioning improves accuracy, but complexity increases as well. The future of trench navigation may involve more advanced artificial intelligence. Machines may learn to interpret sonar echoes more effectively, distinguishing real obstacles from noise. Improved battery technology may allow longer missions. Stronger materials may permit deeper dives. Each improvement brings us closer to fully understanding these mysterious regions.